Well, honestly, I think we can start and make it informal. Okay, so I'll start with the question. Okay, so what I will speak today is about finite elements. Okay, Kratos can do something, some other things that are not finite elements. For example, they implement DEM as being implemented. Maybe you could do volume of fluid. But dynamic is all about data structures. Okay, but today I'm going to focus on finite elements, and I will consider IGA to be a subset of finite elements. Maybe it's a lossy definition. I understand that's not exactly the same, but that's how it works. So my question to you is, if I have a finite element code, what do you think are the most important things that you need to do? In a finite, what is that you do in a finite element code, the essential operations?
Assembling the dimensional fusions.
So you use the keyword element and use the keyword assembly. Okay, so in essence, you will have to find one way to take your physics, to transform that physics into a right-hand side and a left-hand side, so a matrix and a vector, essentially, and then put those things into a place in a big matrix. Okay, a big matrix that you will want to be sparse in order to take advantage of the. So I was just starting right now. In order to do this, you need data. Okay, and what sort of data do you think you may need from a node, for example? Maybe I'm already biasing the answer. But okay, you have an element. What does an element need in order to construct in general, okay, independent of the physics? But what sort of things do you think that will be needed in order to construct the
nodes, coordinates, connectivities?
You will need the nodes coordinate, the connectivities, and when I say the connectivity, it's really the topology. So having 4 nodes is not the same if you have a tetrahedra or if you have a quadrilateral. It's still 4 nodes, but they are connected in a very different way. So that's the concept of topology. And what else? Then you will have some properties and maybe some place to store your nodes, right? So maybe on the nodes, you may have displacement or temperature or whatever, okay? Well, the Kratos tries to do this using object-oriented programming. So essentially, all the items that you may eventually want to use are objects, say Kratos. So there will be an object node, which is a control point, really, in IGA. There will be an object that we call geometry. Geometry is the topology of the connectivity. Let's say it tells how things are connected. Then there will be an element that constructs on the geometry, and the geometry at the very end is a list of nodes, pointer to nodes, augmented by information about how they are connected. Okay. And there will be an object in Kratos, it is called the builder and solver, that eventually takes one small matrix and writes it into the big one. Okay? Now, the very first thing that one asks to himself when you want to write or when you design for finite element code is what exactly I want my element to give me. Okay? And I understand that this is not well explained, but let me try to, well, I will try to do it here so that it is eventually visible. I'll open one moment. So in essence, you have 2 options. Of course, you have very many options, but one thing is what you study when you go in your very first code of finite elements. They tell you that eventually you will assemble something that is like a matrix K times U equal to F. Okay, maybe it is a thermal problem, maybe it is about structures. It doesn't really matter to me at this moment. But at the very end, they will have one left-hand side, and they will have this, both the K and the F are constructed by finite element assembly, and U represents your unknown. Now, this is nice if the problem is linear, and this is what you will find in any textbook about finite elements. Your first textbook treats a linear problem. It tells you a recipe to construct K and F. And you know that, all of you. Now, what if the problem is non-linear?
The tangents.
Well, yes, but the tangent is really a tool for you to arrive to the solution. In particular, if the problem is non-linear, you cannot write it this way because this is an expression that is intrinsically linear. Okay? Instead, so this is good for linear problems. If your problem is nonlinear, well, what we know how to do is how to minimize a function. So we need to define a function to minimize. What is the function we want to minimize in our recipe? The residual. Turn it on. So what we will do instead is that we will define, instead of defining this, we will define a function residual of u, which is equal to f minus k of u, for example. Or if you like, speaking about structures, that would be equal to the external forces minus the internal forces, which may eventually depend on you. Also, the external forces may eventually depend on you. Okay? Now, why am I spending my time on this? Because now what you may want is that you can have some portions of your domain that are linear and some portions of your domain that are non-linear. Now, what is the happen? If you have a nonlinear problem, then you have this thing here and you want to minimize. And as your colleague is telling, normally, many times you will attempt minimizing this function by using an interruption technique. So out of this, well, maybe we'll end up solving something that looks like this. So you have a U-old, that is the last thing you know. You find, it differentiated, okay? Then this guy here is your matrix A, and this plays the role of F. Except that you now solve for a correction. You don't solve for the full U, okay? Well, once you have the U, then you say that U next, or U new, the one you will use in the next iteration is equal, maybe it's too big, the line, but U old plus the U. The U that comes out of this, of course, okay? Something more normal, this. Now, what I was telling. Now, imagine that I have something like this, and I want this portion of the domain to be nonlinear, but for the other part, I want to use a linear element. Example, this is a part that may plasticize, may have a plastic behavior or a damaged behavior, but you want to have the other part linear, okay? Well, you know, if for the linear part you use this approach, and for the non-linear part you use this approach, you have a problem. Why? Because in one case you solve for the full U, in another case you solve for the U, okay? So it's something that looks the same once it is assembled, but the meaning of what you solve for is different, okay? Now, you do want to be able to have a linear part and a non-linear part in your meshes or in all of this, right? It is something that you do very often. for a lot of reasons, okay? How do you think you can cope with the two things to allow this in your code? Well, one way is that a linear problem is a subset of a nonlinear problem, a special nonlinear problem. It is a nonlinear problem that converges in one iteration because the tangent stiffness matrix is exact. What I'm trying to tell, and actually I cheated because I already wrote it here, that if your problem is linear, you can write this thing here. You can write, instead of f, you can write f minus k times u. However, you will have the property that if you apply, if you take the derivative of this guy with respect to u, the derivative is exactly k. So when you apply this idea, so in application to a linear problem, well, what you get is k times the u equal to f minus k u old. And you have the property or the guarantee that independently of the value that you have for u old, in just one single iteration, you will find the u that corrects u old to obtain the value you want to get. So what I'm telling is the Newton-Raphson technique can be applied to a linear problem, and it gives you an exact solution in exactly one iteration. The reason for which I am telling is that since being able to doing this was one of our design objectives, we decided that in Kratos, everything is written as a nonlinear problem. So you never write this. So this we do not write. Instead, we always define a residual, and we always define, I would say, we always define the tangent matrix, at least an approximation to the tangent matrix. If it is the exact one, better. You will accomplish the convergence properties you expect. If it is not, eventually you will converge slower. Okay? Now, how do I apply boundary condition? In particular, how do you apply the Dirichlet condition? I'm speaking of finite elements for the moment. So, assuming that you have the Dirichlet, the delta Kronecker property for the your unknowns.
Mostly you apply strong.
Correct. But so let me paraphrase my phrase. How would you apply the boundary condition if you were here? And how do you apply the boundary condition if you're in this context?
In this case, you said that it was optimal to reach the condition.
So I'm going to treat first the linear case, but this is not what we do. I just want you to see the difference, okay? Because that's key. That's one of the things that so I need to do like this. I need to add another page, and I need to maximize it again. So linear case, Dirichlet conditions. Linear case. So in the linear case, I will divide my matrix as K internal, K internal Dirichlet, K Dirichlet internal, K Dirichlet. So this is U internal. That's really the unknown I want to solve for. And this is U Dirichlet. By the way, you should have a presence sheet which you may pass. I mean, I need you to all sign it. So this is the linear case. What I'm telling you, this is not what we do in Kratos. Now let's imagine that for any reason I want u directly, that's a vector, but to be equal to 5. Okay. Well, your answer is correct, but it's not complete. Let's say yes. So what you studied in a textbook is that you would take I stands for internal, so that's not the one you really need to solve for. Well, in a sense, you could say this is a 0, this is a 0. I put an identity in here, okay? And now this is my u internal, this is my u Dirichlet, and then here I have b internal, and this is a 5. Is that correct? That's what you meant, I think, more or less, right? What am I missing?
So you should eliminate both columns and rows.
Well, I did eliminate column. This is u Dirichlet, so I eliminated this and that. Well, okay, you're saying that they should not solve for it. I mean, they should not be in the system. You are correct. It is possible. It is what we call the elimination builder and solver in Kratos. Okay, that exactly does not assemble those. You will have only this. But logically, it is this. The point is that what you have here is not correct. I'm making a mistake. What is the mistake?
You have to do minus.
Correct. You have to do minus. So, I mean, here you have to do, well, plus, and here you will have minus KID times, well, 5, really. So the value of the Dirichlet you want to do, and that's a 0. Now, this problem, once you modify BI by adding this, then you're achieving what you. Now it is correct. Okay, that's maybe a detail, but do not forget, because otherwise the result is wrong. Okay? Well, take a look. This is B minus K, the U you know. In a sense, it is like the residual. Okay? But what you will achieve is that if you solve this problem, then UD will be equal to 5, and UI will comply with the conditions. Well, that's good. Non-linear. What can we do in the non-linear case? Anything? You still want it to be strong. I mean, we have the delta Kronecker property of your shape functions. You still want to impose it strongly. So you don't want to add a penalty or some sort of sophistication, because that would imply modifying your weak form. So you don't need it. I mean, at least you don't need it here. You can make it more automatic. Any hint? Well, what you can say is that when you are in a nonlinear case and you're always seeking for a correction, okay? But what you really can tell is that your U old is also composed of U old internal and U old Dirichlet, okay? But the point is that U old Dirichlet, you know the value, so you know exactly the value. So for the essentially, you can tell that for this guy here, you can already apply the value you want. So you can say that your U old is really U old I and 5. I tell a vector of 5 just because I want to apply 5. Okay. Well, what I'm trying to tell is that if you now compute your residual, so if you now go and you want to solve your KII, KDI, KID, KDD times DU I DU Dirichlet, my residual internal will contain already U all the I, but it will contain U all the Dirichlet. And this one contains already the 5 I wanted. Okay? And then here you have your residual Dirichlet, whatever. Okay? Well, why am I telling? Because since my U order I is known and it has the correct value, because I know I can already apply it. Since I have the knowledge of what I want to apply, I can put it directly. Well, this simplifies. This simplifies because what I want to accomplish is that DUD is equal to 0. I do not need to correct the U Dirichlet because it is already the right value. So what I want to impose onto this system is that DUD is equal to 0. The reason for which I am telling is that now I'm going to do the same trick that I do here. Okay? So I take exactly the same idea. I still have KII 0, 0 I times DUI. That's what I want to solve for, DUD. But here now my DUD is 0. Okay? And if here I add the residual, and I would have to remove minus KDI, sorry, KID times 0, because I know that the value I'm imposing is 0. So this guy goes out. I do not need essentially to make this multiplication because it's a multiplication by 0. Okay? This is what we are doing. This is the approach we are following. You see? That's the... Now, what your colleague is telling is correct. In real life, if you know that those values are fixed, then you will not assemble. You can organize yourself. So, I mean, you know that this is 0. I can only build this part and that part. I'm telling you, it is indeed. It's called the elimination builder and solver. There are essentially two. What is the issue with doing this? The feature of this approach. The feature is that you are building the fixity that you have in your system into the structure of the system. If at any moment you want to change the fixity, you have to change the graph of the problem. The advantage is, on the other hand, that you're solving a smaller problem. Clear? Okay? One other feature of this is that imagine that you want to fix just the UI. The UX is a structural problem. You just want to fix UX in one node. Then you will have your nodes are UX UI, in 2D, UX UI, UX UI, UX. You have one of the nodes that just has one unknown in this reduced system. That's fine. If you use a direct solver, there is no problem. The problem is solvable and everything. The problem is that if you want to eventually use a precondition, in particular based on multigrid, they need that every block of unknowns has the same structure. So you need X and Y on all of your blocks. All the blocks need to be the same size. Now, the question is, but do I want, is it so important to use multigrid or to use this sort of solvers? Well, we are the fastest. Okay? So sometimes, and many, many times in Kratos, you pay the price of actually having those diagonals, okay, with the zeros, in order to, on one side, being able to use a multigrid, and on the other side, in order to be able to change the fixity without having to reform the graph, the the non-zero structure, the non-zero factor of your matrix. Okay? That's your decision at the very end. But forming the graph is an expensive operation, very expensive. It is more expensive to form the graph, to tell where the non-zeros are, than to eventually fill the non-zero, to compute all the elements and to assemble them into the correct place. Okay? Well, what about reactions? How would you compute the reactions? I mean, yeah, I have a fixed value, and a fixed value means, if you speak in terms of forces, that is more or less in our background of all of us, then it really means that you're looking for the force that is needed to apply onto that node so that the value is what you want to impose. Okay? How do I compute the reactions in this case? You see what you understand the question or no?
Yeah, after solving the problem.
Right. Now I have my U, but how do I compute the reactions? So my U now is known. The reactions are nothing else than the residual, minus the residual. Okay? So the very same function that assembles the residual can be used to compute the reactions. However, the residual will be 0 everywhere, because what you did in here is that you looked to the value of your solution that made the residual to be 0 on all the internal nodes, but not on the boundary nodes. On the boundary node, it is 0 once you adapt the reactions. So minus that, it would give you the reaction. Okay? Well, I'm just telling because it is important to. Okay, now I'm going to show you very soon what is the or how and where this is implemented in practice. But I already told you about this graph. Okay, so let's think for a moment, how is the finite element assembly, or how is the concept? I know you're familiar with it, all of you. But the idea is very simple. I take a matrix and I just put my contribution sum, my contribution there where I want it to be sum. Okay? Simple, very simple. Now, the point is that if you think at what happens under the hood, you don't have a matrix with all the zeros. I mean, you cannot write at any position. You first have to tell where the positions I'm going to write to are, because you're going to allocate a sparse matrix that has a place to store your contributions. I don't know if I am explaining myself. What I'm telling, imagine that I have, I mean, that's a 1D Laplacian. So 1D Laplacian is, we'll have a form that looks like 2 minus 1 minus 1, 2 minus 1 minus 1, 2 minus 1 minus 1, 2. Okay, it's a structure like this. And then, I mean, this is a line that is order 0, 1, 2, 3 to the end. Okay? When you write your finite element assembly, you know beforehand that this is a 0, this is a 0, and so on and so forth. So these zeros, they are simply not there in the memory, right? I mean, understand that's and not buy it, okay? However, from the point of view of coding, you need to tell then what are the positions that are non-zero, because the kind of data structure we use for the matrix, we will spend more time on it tomorrow maybe. But this one that only contains, is only ready to contain few non-zero. It will be almost empty. Do you remember or do you know what data structure is normally used to store the matrix? what is the matrix storage format. Normally, in the vast majority of finite element codes, you store matrices. This is stored in CSR format. The CSR format is a format in which you have 3 arrays. Okay, whatever. That's a format that is designed to allow fast matrix vector multiplication. But it is a format in which you need to say beforehand that I have the position 0, 0, the position 0, 1, but not the position, all the other positions in the row. Well, one of the important steps, one of the difficult steps to do is that you will have to look through your connectivity. You will have to ask one of your elements what are the unknowns that you eventually want to solve for. Okay? Then you will have to create a list of all of those unknowns. You will have to assign a number. And then you have to represent the connectivity in terms of a graph. Essentially, what I'm telling, you have to tell that the degree of freedom Ux associated to node 1 is connected to the degree of freedom Uy of node 22, because that means that they have a non-zero entry in that matrix. That is another representation, a graph representation of the connectivity of your finite elements. Okay? A graph is nothing else than the ij's that are here in this. Is a representation of the non-zero ij that we have in here. Well, one of the important stages of your calculation is that you build this graph. This graph normally, but not always, speaks throughout all finite element calculation. This is not necessarily true. For example, if you were to split elements to tell at a certain point that this node and this node are not any longer the same node, they get disconnected, then the graph would change because the topology of your domain changes. But in principle, in very many of your calculations, this will be fixed. Okay, and so we will want to compute the graph, store it once, and then reuse it very many times. Okay. Okay, but this ends the theory. Okay, so well, theory. I don't know if this is theory or. Let's just try to see how this is organized inside Kratos. First of all, let's start it from there. We will need an object that is in charge of asking to the elements what sort of connectivity they have, and it will have to ask for the k and for the left-hand side and for the right-hand side, right? So this object in Kratos is called a builder and solver. Builder and solver does 2 things. Well, 3 things. Constructs the graph, assembly does the finite element assembly, and calls the solver. It does it together, the builder and the solver, because there are some things that are tied, or there are some sort of solvers that can be done element by element, or there are some things that you may want to do. So it gives you a place to eventually implement those things, even if in general you will not need to have it.
Can you elaborate a bit more? What's a graph?
Yes.
Maybe with an example.
Okay, this is indices. So the i's, so the j's go in this direction, the i's go in this direction. Okay. I will not give you a mathematical definition of what a graph is. Okay, that's not a mathematical one. So, but let's say that this is 0, 1, 2, 3, 4. This is also 0, 1, 2, 3, 4. Now, node 0 I mean, node 0 is connected to node 1. I mean, degree of freedom 0 is connected to degree of 0. Sorry, 0 is connected to 0, to himself. 0 is connected to 1. Okay? Now, 1 is connected to 0. So 1 is connected to 0, 1 is connected to 1, and 0 is connected to 1. Sorry, I said it wrong. I said it wrong. 1 is connected to 0, 1 is connected to 1, and 1 is connected to 2, because that's this entry. So essentially, it's the list of all the connectivities that you have, of all the links between entries in the graph. It is, these are the entries of this. Do you follow, or? Okay, maybe you don't follow. Let me try in a different way. I don't know why I numbered it this way. Sorry. So 3, 4, 5, 6, 7, 8. Let's see what you have in an element. This element, it connects 0, 1, 4, and 3. This one. Okay. This one connects 1, 2, 5, and 4. I'm looping in this direction. This one connects 3, 4, 7, and 6, and this one is 4, 5, 8, 7. Okay. Now, this is one way. Every element connects what it connects. But now I ask you, node 1 belongs at the same time to this element and to that element. But a change in the value of 1 will change the value of the residual in all the nodes of an element. Of which element? Of this and that. Okay? And also the stiffness matrix, possibly. Okay? Then node 1 is connected to himself, but also to 0, to 2, to 3, to 4, and to 5. So the connections that node 1 has are all the ones that are in the neighborhood. Once I sum my matrix to this, I know that the entries, I need to pre-compute the entries in the matrix in which I will need to add my, and they're those. They are the ones, the connectivities, let's say, but the connectivities intended as entries that are connected through an element. Okay? Does that make sense? Or that's anyway. So I was telling a builder and solver. I need your signature on this. And this is your signature. We will not publish it. I mean, it was not reported yet yesterday. Yeah, that's sorry. Anyway, it will. No, I think it was not recorded. It was shared, but it will not be shared to the community in any case. That's. By the way, since you are all here, they asked me, because I took 2 pictures yesterday, if they can put it on the web, if you agree or if you have any problem with that. Yeah. Yes? No. Okay. That's the ask me to do, and I will tell there is no problem. Okay. Back to the builder and solver. Builder and solver, there are at least two. There are more really. What are those? They are the elimination builder and solver. Well, BS. This I have the temptation to wipe it with my finger, which doesn't work, of course. And the block builder and solver. BS is not bullshit. It's builder and solver. Okay. But there is something important. The versions that we have like these, they work in serial. And when I say in serial, I mean in symmetric symmetric multiprocessing. I mean, it is, if you have multiple CPUs that have shared memory multiprocessing, whatever, SLP it is called, and I'm not sure what it is the acronym of, but it will use if you have multiple cores at the moment of assembling the thing. But there is also a version. This is a serial version. There is another version of those that is distributed. It is exactly the same features, but it is distributed. That is, it works in MPI. Okay? They look the same. They are essentially a function build and a few other functions, construct matrix structures, and a few others. I'm going to show you where. If you want to correct, tell something that you want to correct, you tell me. So if you go inside the Kratos, there is a directory solving strategies, and there are some builder and solvers. They are block builder and solver and the elimination builder and solver. These are more or less the important ones. Now, if you go in the base class to see what is the interface, this provides a few important functions. I will show you just the important ones. But it is builder, and it has, you can either build everything or build the left-hand side or the right-hand side, and build and solve. This, at the same time, does the build and provides you the solution. Okay? Well, this is more or less the important thing we have. Then there are others that are devoted to applying constraints. I will speak a bit later about constraints. Okay? But then there is a function that is setup.set. And the function setup.set is the function that goes through all of your elements, okay, and asks to every element what are the unknowns that will be eventually needed. This serves to compute the complete list of unknowns, okay? And then there is a function that is construct matrix structure. Well, setup system, but it is very related. Will eventually be here. Well, there is a function that is construct matrix structure that builds the graph. Okay. What else do I need? This is the tool we use for assembly. Just try to think. What else do you think is needed? There is a linear solver. A linear solver will essentially have a function that is solve A, X, B. So, I mean, it does the inverse. What else do you think we need in a finite element code? compute reactions is a part of the difference solve. You will need to implement something like either a linear strategy, which does one iteration, or a Newton-Raphson strategy, or some sort of quasi-Newton strategy like line search, or okay. So what you will need is a solving strategy. Examples of these are the most important one: linear, Newton-Raphson, and maybe line search. Okay? There can be others. So you have the right, so you can, it is designed so that you can implement your own. You can do very complicated things in there. But the generic one are more or less those ones. Now, if you have a nonlinear problem, you will have to know if it is converged or not. Okay? So look what, there is another object that is a convergence criteria. And all of those, they require a tool. And the tool is the linear algebra. Okay? So as of now, they use below as a support structure, they use all of those. They depend on a space. And space is the space of linear algebra operations. So essentially, maybe it is a bad name, that's what we gave anyway, but it tells what kind of matrices you're using under the hood and how to implement things like multiplication between matrices, like adding into a point into the matrix, this sort of things. Okay? Well, with all of this, it will be more or less fine. But there is one last thing. And it is, imagine that you have, I will speak about a structural problem again. Let's now imagine that you want to deal with a static problem or with a dynamic problem. Okay? So in a static problem, what you want to have is that your residual R of U is equal to F external minus your internal forces which depend on you. Okay? That's residual static. In a dynamic problem, well, what you will have is something that is residual dynamic, which depend on you, will be equal, for the same problem, F external minus the internal forces that depend on you. And now what you will need to have is the inertial forces, let's assume that the mass is constant, minus the mass times the acceleration minus the damping times the velocity, for example. Okay? Now, what you want is that your element, I mean, this guy here, obviously, this is nothing else than the residual static of you. Okay? You don't want to have an element that does dynamic and another element that does static, right? So you want some tool that asks to the element either just for the static part or also for the other things that you need, and eventually to put them together. Okay? Once you do that, you have different options. You may, for example, build up a global mass matrix and then do the multiplication by the acceleration, or doing this element by element. Okay? Well, in Kratos, there is an object. This object is called scheme. That is a sort of man in the middle between the builder and solver and the element. So instead of the builder and solver asking to the element for its stiffness matrix, for example, the builder and solver asks to the scheme for the stiffness matrix, and the scheme in turn will ask to the element. Okay? Why so? Because at this point, once I add for, well, the residual, for example, if I use a static scheme, I will ask only this thing. If I use a dynamic scheme, I will use all of this. So scheme stands for time scheme, really. Okay? Of course, if you use backward Euler, no, not backward Euler, if you use Newmark, or if you use, I don't know, some sort of generalized alpha, maybe the way in which you either calculate accelerations or you use the mass matrix may be different. So you have as many time schemes as time integration schemes you want to have in your solution. Okay? Well, so the collection of the space as a tool to do things, builder and solver, linear solver, solving strategy, convergence criterion, scheme are more or less all the objects that are in charge of doing the finite element things inside Kratos. Okay? I will not at all look into how they look like, but they are all in the same folder, and they are in the folder of the solving strategy. Okay? What is the time, by the way? Perfect. Now, the other thing that you need is to understand a bit, or at least to have a glimpse about how things are stored inside Kratos. And first of all, it is important to understand that Kratos it can do explicit, because, for example, you could do an explicit solving strategy that at this point maybe never builds the matrix. Okay? It only builds the right hand side. It can be done, it has been done. Right? But the bias of the Kratos is towards implicit solution. It doesn't mean that you cannot do explicit, but it is optimized for flexibility, let's say so. It is optimized under the idea that most of your time will be spent in solving the system of equation rather than in building the. This means that our data structure tend to be flexible, but maybe they are not as fast as the one you would choose for an explicit code. Okay? That's just a warning, okay? So we normally, our bias is toward implicit things, okay? Well, our elements, I told you before, so now I will go back a bit to wait, what did I do? I'm not very good with this. We can survive. So now we are speaking about the element. So let's think to what are the things that an element is. And I said it before. An element will have a geometry. And the geometry, what is really is a list of pointers to nodes plus information. And when I say information, I mean routines to compute shape functions. It is not only this. A geometry can also store things. Oh, sorry. geometry has a database, so you can type element whatever, get geometry, and then on get geometry, set value, temperature if you like, or young modulus, or whatever you like. Any variable can be set onto the geometry and it will be stored. Okay? When I say that every element has a geometry, every element has a pointer to geometry. So the same geometry may belong to different elements, or you can have two different elements that have the same geometry. What is this for? Imagine that you want to do thermal and structural. Okay? You may have a thermal element, you may have a structural element. Okay? Well, the thermal element was implemented by Charlie, the structural element is implemented by me. If the two elements share the same geometry, every information that is available on the nodes or every information that is shared on the geometry is visible to both of them. So they are eventually able to take from it. They don't need to take, but eventually they can. You understand what I... You have a comment, Manuel? Okay. So also the ones that know, feel free to add to what I'm telling you. It is. So the database is flexible in the sense you can set more or less anything, any Kratos variable. Indexed by variable. The geometry also has integration rules. This is maybe something that yes.
Just to add that you need to know before the simulation which variables are you going to use. You can add them, but you cannot change them. Okay, so when you add it, that's fixed. You cannot go in the middle of the simulation and say, okay, I know I need another variable. I will add it. It will not work.
That's correct. Wow, this is, I brought it so bad this that it is not possible to read it. So. You can also do it somewhere else in integration rules. The expert in integration is Manuel. But at least for normal element, once you define a topology, there is also the information on how to compute Gauss integration or some different type of integrations in that. Okay. An element also has other things. Also has a pointer to properties. And what is the properties? The properties is intended as the material, let's say, to store the material database. Okay. So while every element has one geometry, a group of many elements, this is shared by many elements. So I don't know. We have 1,000 elements that are made of steel when we have one property. Another 1,000 that are made of something different. A properties also has a database like the one of the geometry. Okay, but it's a different database. So you always can retrieve things from the same point in which you put. If you store something in the properties, you have to retrieve it from the properties. If you store it in the element, you will have to retrieve it from the. Okay? And potentially, well, potentially, it has a constitutive law. And the constitutive law is, in essence, what defines the relation between the input strain and the output stress, which you're allowed to choose in which stress measure and strain measure you use. So the interface is a bit complicated. It is documented. It is in the wiki. Okay. And it also computes C, which is equal, defined, or at least intended to be, the derivative of sigma with respect to epsilon. When I say sigma, take it as the stress measure you're using, and epsilon as the strain measure you're using. Okay? So it could be Viola-Kirchhoff against Cauchy-Green, whatever. That's the thing. Okay? Together with element, or parallel in a parallel world, but with essentially identical interface, so identically that eventually we will make them to be the same thing, even though they will go into different lists. We have condition. Interface is identical, but element is intended in its design to be used for volume integrals, let's say, or integrals over the body of your domain, and condition for boundary condition, like Neumann boundary condition, things like that. The interface is essentially the same. Okay? The element has a very rich interface, but in essence, it has a function that can allows you to compute left-hand side and right-hand side. It has a mass matrix, which you can optionally call. I mean, it implements, and it is there if you want to call it. And it has a damping matrix too. Okay. It has the database, so you can access to the geometry and the geometry of the database. And important, it has two important functions. This is not stored, but these are important functions. It has one function that is equation ID. And I don't remember the exact name. Maybe it's not, I don't know if this GECKO sys, it is, I can check, but listed of the list of the degrees of freedom that you will eventually use in the element. I don't remember the exact name. Do you recall it? GECKO list. Okay. What is this for? For example, a thermal element with 4 nodes will tell that I have, for every node, for node 1, I have the degree of freedom temperature. We will need to tell what the degree of freedom is. Okay? The important thing is that it tells how it is organized internally. Example, imagine that you make a structural elements. You could have the x dy dz, then the x dy dz, then the x dy dz, or you could write the element as dx dx dx, dy dy dy. This tells to the rest of the world how you wrote your element. You see what I mean, right? So that the builder and solver then will build it in the right positions. Okay? A node. A node has a lot of things. It's a heavy object in Kratos. It has x, y, z current coordinates. Okay? Yes, x0, y0, z0 original coordinates. And original coordinates, I mean, the coordinate of a node at the moment at which you deform and when you construct it, they may be different. In particular, for example, if you are in dense deformations. Okay? geometries compute things always based on those. Okay? It is up to you. It will be done in the schemes that are already implemented to tell, for example, that x is equal to x0 plus displacement x. Okay? But we have both displacement and the original coordinates, because when you want to write a thermal element, you don't want to know the displacement is. You directly look at the position that you have currently and you just work on that. Okay, so you need the two things. What else? It has a database with history. A database with history, what do I mean? I mean that you can ask to a node, give me the value of displacement in the current time step or in the past time step, or maybe 2 steps in the past. Okay? Can I retrieve if I have 1,000 steps, 1,000 steps back? No. There is a buffer size, number of steps, limited by buffer size. Okay, so these are things like this. It has a database without history. What I mean with without history is, imagine you want to color a node. You want to tell that a given node has house index. That's a different, I don't know, an identifier that you want to add there and will always remain the same. Then you don't need to have a value that changes with the story, let's say. The one in the past will be equal to the one in the current set. Okay? So you have two different databases, one that has history and one that doesn't have history. Okay? It has flags. And flags are essentially, there is one double in which you can store 64 flags. They're just bits, okay? From a closed list. So there is a list of flags which is available in non-Kratos. By the way, I should have said that also the element, well, really the geometry has flags. Okay? I'm just thinking, yes, and it has a list of doffs. So what is a doff in Kratos? A doff is a pointer to a position doff. Okay, it is a pointer to the database. So if I tell I have a given doff, I can retrieve the value of the database that corresponds to that.
So doff is another option.
Is another option. And it has more things, which I'll tell right now. What I'm telling is the following. If I have displacement x per se means nothing. But when you say that this is the displacement x of node 22, then it makes sense, because now you can go to the database and you can point directly to the value there. Okay? The doc will do that for you. But it also has other things. In particular, it has equation ID. And it knows its reactions, reaction type. And moreover, what you're able to construct list of dots and you're able to order those. So you're able to compare two dots and say dot temperature of node 32 is larger in some sense, so there is an ordering criteria to tell if dot temperature of node 33 is before or after pressure of node 1. That's not obvious. There is a criteria for doing that that allows constructing lists, ordered lists of this. Okay? And I would say that this is more or less all what we need for finite elements. Let me think. Am I missing something? Am I? Okay. Now, how are those things? Sorry? Now we need to tell the containers, not the data structure of how they are contained, which is something we may discuss tomorrow, but at least organizationally, where are things? Okay? Okay, so we have a lot of elements, we have a lot of conditions, we have a lot of properties. Well, we need to store them somewhere. Where? In a model part. A model part contains list of elements, list of conditions, list of properties, and a list of constraints, really. It also has a database and a list of submodel parts. What is a submodel part? A submodel part is another object model part, okay, which contains like a portion of the elements, nodes, whatever, that are associated, that are tagged in a different way. Yes.
So, Ricardo, all these things you're mentioning are kind of attributes to the model part?
Are members of the class. So these are a vector of
list of vector pointers to the vectors. So I'm not object per se. List of.
So it's a vector of pointers to object, to elements, for example.
Probably you have to mention that we also have measures.
Sorry?
If we're going to explain something about MPIs, we also have a list of measures.
I will maybe tomorrow. Okay. It also has a communicator. This, yes. Which is the object that handles MPI communications. Okay. I mean, this. I just want you to try to get the logics, okay? Because it is there, and if you, I mean, eventually we can point you to where it is, and it is quite automated class, okay? In the code themselves. But in essence, what I am telling is, if you have a model part, you have a lot of things. Now, what are those submodel parts for? Let's imagine the following. You have an object like this, okay? Now, you have the volume, for example, that contains everything, everything. All the nodes in your model part are contained in a model part volume. But then for any reason, you want to have the list of the nodes that are here, okay? Because, for example, you want to apply, it's a fluid, you want to apply an inlet condition, okay? So this is inlet. what you have is the possibility of telling the inlet is a collection of nodes, has no elements, for example, but has conditions. It has condition and nodes. And now you can ask, give me the submodel part inlet and give me the list of nodes that are on the inlet. And now you can look on them or you can do things. Okay? This is important because this way you can do operations, you can apply a process, you can do things on that. Okay? If it doesn't make sense, I'll stop. Okay? I mean, if you need to discuss something. I can have as many of these, and they can be hierarchically. So a submodel part can have a sub-submodel part as many levels below as you like. You have one guarantee, and it is that if a node belongs to a submodel part, it also belongs to the father. But the same node can belong to multiple submodel parts. Example, I may have inlet and skin. So a node that is here belongs at the same time to the inlet and to the skin, as well as to the volume. Okay? It's just a way to catalog things. Okay? You follow? Well, and do we have a single model part? No, we can have multiple model parts. Example, imagine that you have in an industrial project that we did, we had a mold, which was where a fluid could flow. It was a casting, it was used aluminum. But then you had the casting mold. So you had the part outside, it was something like this, imagine. This was here, the fluid that was being calculated, but then we had something on the outside, all around this, an object like this, where only the thermal problem had to be computed, okay? Because that was designed to, I mean, to see how this was getting colder, okay? Well, so model parts can be multiple. This is one model part. This is another model part, okay? So a list of model parts is contained in a model, in the model. Model, there is just one. And the model contains list of model parts. Okay? Maybe. So this is contains list of model parts. Okay?
So the submodel parts, they don't have much, like they don't have responsibilities same as the model part.
They are model parts. The object is the same. So if the type of object is the same, the interface is identical. Just they know if they are root or not. The root model part. So once you add a node to a submodel part, automatically it is also checked if that node belongs to the father model part. If it is not there, it is added. Okay? And this happens recursively. Okay? Well, model is the biggest container that we have, and it is, it is what contains everything at the very end.
And both model and model parts are classes.
Model and model parts are classes. Model handles the lifetime of model parts. Okay? So that's, if you want to create, the model is created at the very beginning, and there is one model in the entire simulation. There is one important point, and it is that a model and a model part can be serialized. So if at a certain point of your simulation you want to freeze the simulation and store it to disk, you can serialize the model, and then you can reload the model. So this can be used either to store your simulation to disk, to freeze it, and to eventually resume, or, for example, you can serialize a model and you can send it by mail. It will be a big file. Okay? But you understand? So you can send it by via the network, if you like. Okay? Any comment?
Well, so,
Please.
so another important thing is to say, because we explained that, for example, model part has a model part, then why don't we use a single model part and we make different model parts? Yeah, that's one question. And that's because the variables that we were explaining to you before, the list of databases that are tied to the model part, okay, not to the model per se. So, for example, imagine that in the casting example that I have explained, the outer part only needs a variable for temperature and deformation, for example, but the fluid part needs the variable for temperature, deformation, velocity, viscosity, whatever. Okay, so you have much more information in one model part than in the other. You put all the variables everywhere, you're going to have end up with a memory space which is much bigger than you need. So that's why we make different model parts, okay? Because in one model part, we're not going to store a list of variables that we need there, and in the other model part, we are going to like store the variables that we need in the other. Okay? Very important in terms of efficiency, okay? For you to understand which is the difference between why don't we put like a super model part that has everything and then divide between other submodel parts, okay? Because submodel parts share the list of variables, model parts between them, they don't need to share the list of variables.
Manuel? No.
Totally agree.
I think that tomorrow I will tell more. I just want to give a glimpse. This is just the idea, then we will delve a bit deeper, okay? But I mean, this maybe now it sounds very complicated, but they are goodies. They are designed to make your life, or try to make your life easier, actually. So, I told you there is a model. There is also an object that is called parameters. Parameters is essentially something that looks like a JSON, that is what you use to pass options. It is a list that can contain anything, okay? It is not performant, so it is not designed to be fast, okay? Nor to be very memory efficient. It is designed to pass whatever, anywhere, okay? For the settings of your code. Together, those two are used to construct an analysis stage, analysis stages. An analysis stage is one part of the solution process. It may be the only part of your solution process. For years, that's been the only part of the solution process. Well, the constructor of analysis stage has model and parameters. That's what they meant with this. Okay? An analysis stage has a number of methods, but essentially there is one important, that is the method run. Okay, the method run runs the entire analysis stage, and this is really divided in 5 steps or 6 steps. Okay, so this run actually tells you how things are done. You will look more into this. Am I right? Or?
All this is in the Python level.
All this is in the Python level, even though if you like, you could replicate it in the C++ level. Okay. It's a stage, so I guess you understand there can be multiple stages, okay? So what we have is, we have the concept of orchestrator, and orchestrator is essentially a sequence of stages. Example, just to understand what is this for, okay? Imagine that you want to first do a structural problem, and then you want to do a buckling analysis or an eigenvalue analysis, whatever. Okay? Well, then there is one stage that is static solution, and then one stage that is eigenvalue analysis. Okay? And this tells you in particular, the one that we have is a sequential orchestrator, which essentially you give a list. You give a list of things that can be, is a list of stages, okay? The only what leaves through is project is the model, and project parameters, okay? The nice thing of this is between one stage and the other, you can dump your simulation to disk. So eventually you can just resume from the state, the point at which you are. Okay? Analysis stage is tries to give an interface that is common to everyone. Okay, but at the very end, you can do whatever you like in there. So that's your main necessity. Sorry. We give you a few very selected functions, very few, well, but maybe. Well, you will speak it.
Yeah, I will show how it works.
So he will show you tomorrow. But at the very end, they are very generic, okay? And the stage, in essence, is a solution step that is self-contained, okay? So you do the reading of your things, and you do the one last thing, okay? And I told you about the submovable parts, then we go for the coffee. Understand this is. We have the concept of process, and we have the concept of operation. In essence, when you want to apply boundary conditions, you prescribe things to be done on a portion of your entire domain. So, example, apply the replay condition, okay? I want to apply the replay condition for the variable displacement or velocity, whatever, where? On, well, where was that? No. On the inlet, okay? So you tell me what operation to do on what data, or what portion of your domain. And you can do, that's the place at which you can implement things. When you define your input, you're telling the list of things to be done on different portions of the domain. This is done because that's a point at which you can customize things. Of course, the application of the replay boundary condition is simple, but maybe you want to apply a table or something that varies by table that applies according to a function. That's a place at which you can customize that. And I think that with this I'm done. That's all what I wanted to tell. Please.
Speaking about the DDD operation, we have like 3 levels of utilities or processes. And the difference is that an operation will be executed only before the analysis stage is executed and after analysis stage has been executed.
Yes.
A process has several points in which you can hook where it's going to be executed, and we have before the solution step, after the solution step, before initializing the solver, after initializing the solver, and an utility, basically, it doesn't have any point in time which will be executed, you have to call it manually. Okay, so that's more or less the difference. Some of them are called automatically by us, and it will be executed if you put the code in the proper book. And the others, you have to decide where you want to call it, and if they don't have any service, but we will add that tomorrow.
Yes. So this is a bit of my view about what I think that you need to know to understand a bit how it works. Do you have questions or things we should describe a bit more in detail?
I just didn't get the difference between the processes and the utilities.
Yeah. When processes, they have like empty point that we will call automatically, even if you don't call it in your code. So imagine that you're calling a function in Python that, okay. So if you make that process and you put that process in the configuration file of the simulation that you're going to run, that process will be called automatically. So the functions that you have defined in those process will be called automatically. And you will see that there is a big set of functions. You use for initialize, there are places which you can put your code. If you don't have utility, there is no place in the project parameter you can put that utility. Okay, so you have to import it everything in Python S3 because you are doing like analysis or whatever inside the stage. In there, you have to call it manually. Let's say I want to call it here, and you have to write the code. With a process, you only have to write the code of the code of the process, and it will be called whenever.
Just to very briefly, okay? But this is the analysis stage, okay? The analysis stage, I told you it has a method run. The method run has initialize, run solution loop, and finalize. And run solution loop then is divided in these functions. Of course, you can redefine it. You can redefine the run, and then it is all on you, okay? But this is the standardized version, okay? The initialize, for example, again, I'm telling what is the standard, then you can do different things. But it does a lot of things like set up geometry model, blah, 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 whatever, okay? These are all points at which you can hook to, you can re-implement just that, for example, to do one thing at one specific point, okay? For example, you can do in your main or.
For example, if you want a little bit up.
Yes.
So if you see there in line 90, it gets a list of processes for the analysis stage and it executes the function initialize. Okay, so that's the difference between utility. For utility, you don't have that with them. Okay, so if you use a standard analysis stage and you put a utility the parameters, it's going to be called because the code is not there. So you would have to direct the solution loop method, re-implement it, maybe calling this, and then add the utility that you want there. Okay, imagine that utility that computes the normals and do whatever. So that's not implemented there.
Yes. And then just to have then.
If you don't want to this particular process to do anything initialize,
Well, that was.
You just leave the function.
Yes. So you can define your own process. There is a catalog of things we defined, but you can define, if you like, a process, you can do it in Python, if you like, or in C++, okay? And execute initialize, as he's telling, or initialize solution start, may be doing nothing. But if you want it to do something at a certain point, you know that without changing anything else, it will eventually run there. You see what I mean? Imagine. A stupid thing, okay? But your temperature is is calculated in kelvins, okay? And your customer requires that to visualize it in Fahrenheit, okay? Then maybe you will need to do something just before the post-processing, so dumping the results to do that, okay? So what is that? In the output solution step, okay? You will have a list of output processes, but whatever. There is a function execute before output step. Now you define your function that multiplies by or does the conversion, and it does it at this point. Okay? So that it is visualized the way you want it to be. Okay? And you just define your own. Okay?
When you mean solution step, is for the whole simulation or just for the time step?
I didn't get you, sorry.
Let's say, what's the meaning of solution step? It's for the whole simulation?
No. A stage is one stage of the simulation. A step is a time step or one in time, I don't know, load increment or you see what I mean? So I will not go through this. I think you have a list of what is being done where. It's those things to carry heavy material below us. It's trembles. Anyway, I will not go through this in detail. You can read it. Okay, that's and I think you have the list of what is done, right?
Right, it should be like a flow of what's from the simulation, what's happening very high level. Like I will not take the details of the linear solver, but you will see the whole process from the we do Ratos to execute main into the simulation.
I wanted to find the orchestrator.
There's next system.
Yes. What is that? I don't remember.
I don't remember it's actually the orchestrator. It has a class or will be directly in the state manager.
Well, whatever. I'll find this out. But doesn't matter. I just wanted to say that the orchestrator, so the organization of the stages is very similar. You have a list of stages, and when you define a stage, you can tell, or you have one place to tell what you want to do before the stage and after the stage. Okay? Example. After a ROM stage, I want to do an SVD of my results to analyze what I have. Okay? That's what you would put it in a folder. Ah. Orchestrators. So, like, I mean, just to understand, this is how the run of a complete simulation made of multiple stages would do. Well, there are things like the settings, whatever, but in essence, you get the list of stages you have, okay? You create the stage, and you run the pre-process, the run of the stage, and the post-process, okay? And then you delete the stage really, but you also have the possibility to store things, so to store the model, to dump the model in here. Somewhere in here. Yes, in here it should be, but you store the thing, you store the model.
A little bit below. And then in the seven.
In the 70, yes, you're right, it's here. Here you're saving the model. So if you're optional, okay, always. But what you've done that far can be stored to disk so that if you like, you can restart from that point. Okay? Okay, that doesn't. What you also have, and I didn't see, most of the big options. So when you have the settings can be validated. So there is a mechanism of validation. And what you do in here is that essentially you don't need to prescribe all the options. If you do not prescribe an option, you will use the default for that. But what this does is at the very end, you can see in a file dump what you actually used. So both the defaults and the things you actually prescribed, and you can eventually check it. Okay. Okay. I think this is all then for now, and let's go to get a coffee that we all need. A ver,
Already used that, so the very comes to today is weird, but I mean, I do know for my I just like right out of the
To be honest, it's the.
explícale cómo se hace el review.
No, I know. I would say.
How is it going with the edition?
No, I think it's gonna combine very fast. I have this sensation.
I'm going to sign that.
Good through it.
They need to be good.
I mean, we already got to the.
Until really close with
Do we need to take anything by? But you can use the simple version. There's the password there. Yeah. No, I can. Thanks. Thank you. It's 9E, 9 capital E.
He didn't want more one. We didn't before.
No, we didn't like what you said.
So yesterday we discussed mostly the theory, how we do moment fitting, how we find integration rules on a, I would say, theoretical level. And today I would like to focus on how we are actually getting from the input, which is our BREP, to a model that's ready for final element analysis. Okay. And this model, as I said, contains the active set of knot spans or elements and cloud, say, of integration points. Okay. I have to mention already that we are not parsing the NURBS-based BREP model. We are parsing it in STL form, which is just a boundary mesh. Okay, so this is triangular mesh of the outer skin. Now, you might argue that, well, now we lose accuracy, right? We don't have the actual exact geometry anymore. But this STL we only use for the construction of the integration points. Right? So in theory, you could still.
Wait.
Yep.
The point is that once you have the BREP model, the STL is called a tessellation. You could do it on the fly.
Yeah. So in any CAD program, you can say export STL, and you literally get it like this. So the boundary mesh, the surface mesh is very cheap. And it's just triangles, and we don't care about the quality of this mesh because it's just the boundary representation. You see, we have very bad aspect ratios. We have large elements, we have small elements. We don't care. We just want to have a good representation of the geometry. And I think this was one of the best decisions in my PhD to go work on the STL and not trying to do all the geometrical operations on the NURBS-based BREP model. And also, if you refine this mesh, it will not affect the simulation time, right? Because we are solving on this. So it might affect, this contains many elements, it might affect the pre-processing time, but it will not affect the simulation time. Because again, we just use this one to find the integration. Okay. And obviously the goal is then to have a CAD integrated analysis of it. As I said yesterday, in all, let's call them again, embedded boundary methods or immersed boundary methods, we have three tasks to solve. First, we need to classify our elements, which means we need to find the active set of our knot spans. And then we need integration rules for the surface terms to apply Dirichlet and Neumann boundary conditions, and for the final terms to apply stiffness matrix and the mass matrix. But what I haven't told you yesterday, we also need some geometrical operations. Yesterday we just saw some integrals, but you need some geometrical operations to be able to actually evaluate these things. Okay. Because obviously we always deal with numerical integration, so we need surface parameterization or volume parameterization to do these, like just evaluate these integrals. So how do we make this actually work? This I introduced yesterday, hope you remember. Did you have any thoughts about this tonight? Any questions that appear? Hope not. But I basically focus on how we solve the moment. Right? But we assume that we know these reference solutions. Right? So just as a recap again, here we have the matrix, a set of basis functions, which can look like this. In 2 and 3 dimensions, you will also have the cross terms coming from the Pascal's triangles. We have 1, x, y, x, y, and so on. And x are the positions which we preset. We do the point elimination and so on. And we solve for the weights. But we need these, they're also called moments. This is why it's actually called moment fitting. We need these reference solutions. So in fact, all this is an optimization, a least square problem, to fit some certain points to known reference solutions. But you could argue, since we need to know these integrals, why are we doing this actually? Because apparently we need an integration rule, another one, that actually requires to get the reference integral. I come to that later, how we evaluate that. But just again to recap, we also did a linearization. As I said, we preset the points. We use a non-negative least square solver such that we get positive integration weights, and we do point elimination. And now, as I said, for the moments, we technically could use any other integration rule that I introduced yesterday. So technically, you could tessellate it to get these reference integrals. You could run an octree. You could use these modified Gauss-Quadrat rules or the equivalent polynomials. But when you use these methods, then the moment fitting is just a tool to find a set of integration points which has fewer points. Okay, so you could tessellate the geometry with many triangles. You get many integration points, and then you compute these reference solutions up to a fairly high accuracy, and then you apply moment fitting to find a reduced set of points to achieve like the same accuracy as these many points that you got from the tessellation. But this is not really helpful because we don't want to do this. Okay? We don't want to tessellate it because especially in 3 dimensions, very difficult to, because then it's not a triangulation. You need an actual 3-dimensional mesh of tetrahedrals of each cut domain. And I can tell you that these domains look very ugly. But we can also use boundary integrals. And this is what we are doing. The idea is that we never evaluate the volume integral to get these reference solutions. We convert it to a boundary integral. I try to explain this in a second. So as I said, we have the volume integrals here. We apply the divergence theorem, and the goal is that we, in the end, evaluate them just by a sum of triangles that represent the boundary, because we have the boundary. Okay. So how does this work? The divergence theorem looks like this. So you have a function f over a domain, in this case a volumetric domain, and you can transform it into a surface integral, which is just over the boundary. Then you have these g's, which are so-called antiderivatives, and you have a normal vector. and we look at this example, let's consider we want to have the volume. Okay, we want to have the volume, then this function is just 1. Then it gives us the volume. So the first entry of G, the antiderivative, is x, right? So the integral of 1 is x. Then we have this domain, and but we only have the boundary. Okay, so we only have, in 2D we have these lines, in 3D we will have triangles. And obviously we have the normals. Okay, and so in the STL we will have surface normals of the triangles, and they always point in outward direction. Just how you know what's inside and outside, you just know it from the orientation of it. Now when we want to compute the volume, and now we apply the divergence theorem just in x direction, we first project the normals to x direction. Okay, so here we have the normals. You would compute the dot product. So the first entry of n times this function, which is x. Okay, but we do it in a numerical integration. This means we take the integration point of that line, which is essentially the length of the line, because it represents the length. And we do the same on this side. Okay. Does this make sense so far? So all we do is we take this integration point times the weight, and our function is x. So this means x is just a position of this point. And we do the same on this side. And we also have the normal directions. And now this one obviously points in positive direction. This one points in negative direction. This means we'll get this volume. So it's actually very simple. Now you cannot only do it for 1, you can also put x here, and then you end up with like 1/2 x squared. It would still work the same. So you can evaluate any basis function. And now the nice thing about our basis function is they're very simple, right? They just 1x, x squared, whatever. So we know the antiderivatives. We can just hard code them. And with this, we can, when we have a boundary representation, we can evaluate any moment fitting basis. And you might wonder why we have this 1/3 here. Do you see why we have this 1/3? Because now we applied it in x direction. But so we only consider this component and the first entry of the normal vector in x. But we can also do it in y direction. Then it looks like this. Okay. So in 3 dimensions, obviously you also have a set component. And each direction would give you the volume. It should give you the same result if you have a good representation of the geometry. But numerically, we just evaluate all of them and we take the average. But technically, you could just put them to 0, remove the 1/3, and just evaluate the first one. But what this now means in our workflow, we need a closed representation of each cut element. Because for the divergence theorem, we need the entire boundary. This sounds trivial, but if you look at an actual element, it results in this problem. So imagine there are more elements, I've just picked one, which is just a box, so to say. Then what we need is this. So it needs to be a closed surface representation of that element, that cut domain. So therefore, we developed an algorithm that first clips the boundary. We get this. You see, it's just a surface, so there's no volumetric parameterization. This one we can then immediately use to apply our boundary conditions. So we use Wicky's penalty and Nietzsche and Lagrange multiplier implementation. And we can integrate those boundary integrals over the clip boundary. And then to apply the divergence theorem for getting the reference solution of the moment fitting, we integrate over this. Okay. Any questions or doubts?
I'm always impressed when I see this. to be honest.
What's that?
I'm always impressed when I see this.
Yeah. So I have to admit, this gave me some sleepless nights. So honestly, to clip the boundary is simple, fairly simple, because my assumption is that this is always an axis aligned box. Because especially in the parametric space, we just have an axis aligned space, right? So we can make use of that. And in this case, we just need to clip each triangle against 6 planes. So we just remove the part behind the plane. But this was the challenging part to close this domain. Okay, then let's compare this approach to, for instance, the classical octree. Because an octree is, I would say, still state of the art in embedded boundary methods. We have 4 different cut elements, very simple one, then this surface by this sphere, a tower, and very complex one on the right. And you see it's not even connected. You can have like detached domains. Then we choose a set of moment fitting basis functions, which are in this case the Jory polynomials, but just think of them, we have a set of polynomials from constant to quadratic functions. And we put them here in this vector, and we evaluate function 1 to function m. Then we compare the boundary integrals versus an octree with 3 different settings, 3 different integration rules. So we try 1 integration point on each triangle at the boundary. We try 3 and 6. And then for the octree, we also have, like on each leaf of the tree, we have 2 by 2, 3 by 3, or 4 by 4 integration points. And to do the refinement, obviously the octree refinement just looks like this. And for the triangles to get a refinement, I just split the triangle into 4 subtriangles. But it's still the same geometrical operation. I stay in plane. I'm not going closer to the exact geometry. Okay? We stay with the same input geometry. And here we have now the relative error of this vector. So the error of these integrals being constant functions to quadratic functions. And on the x-axis, we have the number of integration points that we need. Okay. For these 4 cut elements. Now, the lines with the asterisks are the octrees. And this is pretty much what you expect from an octree. You get a certain convergence rate, but if you have, for instance, so it works quite well in this case for the tetrahedral and the sphere, and it's almost as good as the triangle with 1 integration point. But for instance, the tower is already pretty bad. And I have to say that the tower is not exactly at like
You can on the screen directly.
So an octree always works fine when you have, let's say, this is your domain, and this is at 0.5, and this is at 0.5, and this is at 4.25. Okay. Now, when you perform the octree, you split it here. Now, this is not cut anymore, but this one is still cut. You would split here again. Put points in here, and in here, and everything is perfect. But now, when this line is just here, you have to refine a lot to capture this. Yeah. And this is what I did on purpose with this tower. So this base is not at 0.5, it had some offset. Okay. And you just stay here, and you see we are already at 10 to the 7 integration points. So many. But what's interesting with the boundary triangles is that when you increase the order of the integration rule, you actually drop by orders of magnitude. So it's in fact better to use 3 integration points on one triangle than subdividing this triangle and using again 1 point in those subtriangles. Because this is what we do when we go from left to right. Maybe now I will actually draw on the 10 for this one. Because for instance, here we also do a refinement, right? We increase the number of colored points, but what we're doing is I split this one just in 4 subtriangles, and I again use a linear integration rule. But it turns out, since we have not only constant functions, but also higher order function, it's better to use higher order integration rules. And with this, for instance, I usually always use even 12 integration points. So you just do the intersection, you throw in each triangle 12 integration points, and you basically can divide the reference solution almost up to the machine position, and even in like in this case. And it's actually not like this STL representation is quite nice, because when you refine the STL, you get closer to the actual geometry, and you also get more triangles. Right? So if you have only a few triangles like this one, then you can only represent what you get by this triangle. But when you refine, you immediately get more triangles. So you have also in the integration point a better resolution of this element. And this is now for quantic moments, so up to p equal to 4, and you get the same. I mean, here I also use, for instance, like 12 integration points. Okay, and I should also mention, in like by default, I usually use, I compute the intersection, and then I run a very basic refinement, and I say I want to have at least around 50 triangles per domain. Okay, just to give you an idea. Okay, then let's look how robust this is, because these geometrical operations can become quite tricky, and at some point you think you found all corner cases, and then you find a new one. So I took almost 5,000 different models from, it's called Thingy 10K database. Here you just see 11 examples. So you have quite simple ones like this one or this one, but also very complex models, especially like this one. And this is the one you saw before. This cut element actually comes from here. Okay. Then I took all these 5,000 STLs and I put our B-spline box around them. For each element, so I think it was 30 by 30 by 30 elements around each STL. Then for each model, I applied the clipping and the intersection. And then I computed the accumulated surface of all the clip sections. And obviously they should result to the overall surface, and the same for the volume. And this is now the surface area. So each dot is one model. Here you just have the number of triangles, but not very important. And this is the relative error in surface area. And you see that for all 5,000 STLs, we actually capture the surface area. It's not like we need an accuracy like this. It's just to show that for all of them, it was robust. And the same for the volume. So what I'm saying is you basically can give quite confident now that you can give the ideal models of arbitrary complexity, and that this will work. So just any questions? So what we haven't talked about yet is actually the first step, the classification of elements. Because it's not trivial to know which element is inside, which is cut, and which is outside. Because we only, in this case, have like the boundary. So we don't know what's their relation with respect to the boundary. And to be honest, the classification of elements is the most important step regarding robustness. So when we look at what happens when so let's assume we falsely classify an element. For instance, let's assume this is actually a larger patch, and this element, in that example, or this one here, are falsely classified as inside. So what will happen is we will integrate these elements. We put them into the global system matrix, and we end up with a singular system. So just one element that's falsely classified will result in a problem that we cannot solve anymore. Whereas when we do a mistake, when we do an error in the trimmed element, it's kind of still okay. Because we will have a local error, but we can still solve the problem. Okay. Obviously, it would be better to do not an error, a trimmed one as well. But just saying the classification is, or the implication of the classification are much more severe. Okay, so what's classically done to classify elements is ray tracing. First of all, the cut elements are easy to find because they are cut by a triangle. You just need to check if that box is intersected by a triangle. Okay, you just check each box against all triangles. Do you intersect? If yes, this element is labeled as being intersected or cut. Then for the interior and exterior, you apply, as I said, classically ray tracing. So the idea is you choose any point, for instance, the center of the element, you shoot a ray, and which is just a line, right? And then you count the number of intersections with the boundary. Okay, so in this case, you have one intersection. And if it's an odd number, it's inside. And if it's an even number, it's outside. Okay. For instance, you start here. This will give you 0. Since it's even, it's outside. If you shoot in this direction, since you enter, you have to exit at some point again. It will give you 2, so it's again outside. Or another example where you have a structure like this. So this will give you 3 intersections, and that's again inside. Now, ray tracing has a problem, or as I think Roland said yesterday, that BREP models are not always watertight. So in many models, you will end up with very small gaps here. It's common to have some flaws in your geometry. Okay. You could also have, if you generate the STL, sometimes you have false orientation of the triangles, or you have a small overlap or small gap or whatever. But now with ray tracing, the problem is since you have millions of elements that you need to classify, so you shoot millions of rays, you will hit through this gap for sure. So that means if you take the ray and you shoot through here, it will tell you this is outside. Or the other way around, this one will tell you it's inside. Then you would consider this element, you would integrate it, and you have a singular system. Okay. So what we are doing is, how can I remove this again? It was actually initially an idea by Benjamin Wassermann, who was a PhD of Professor Lang. We group our elements where we apply a so-called flat fill algorithm. And flat fill is, for instance, what Windows Paint does when you want to, like, you have this little bucket and you say, okay, this area should be now all green or red. Because what it does, it will start at 1 pixel and will just flat that area and move to the right, up, left, until it hits on the boundary. And we apply the same here. So we start, for instance, with this element, and we start flat filling, and the cut elements are our boundary. And then we move to the right, we move down, we move up again. So this is a recursive algorithm until all our neighbors are part of the group or they are cut. So with this, we first classify the element, but we still don't know is this group inside or outside. Then in the next step, we look at all elements that have a neighboring cut cell. Okay. So that means we would consider this one, I guess. This one neighbors a cut cell. This one, this one, this one, and this one. This one does not neighbor cut cell. We only consider neighbors that share a surface, not a point. And for each of those, we do the following. I told you already that we have to clip the boundary anyways, right? This is what we need, also need to get the intersection. So we use the clipping to more or less partition our problem. The problem is when you apply classical ray tracing, for each ray, you have to test against all triangles in your model, which can be quite expensive. So in this case, we will clip the boundary of all neighbors. And for instance, let's say in this triangle mesh, we have 500,000 triangles. The clip one will only have 50, let's say. Right? So a very small number of triangles. And then on this level, we now apply our ray tracing, but locally. Okay. So again, we shoot the ray. We shoot, let's say, 4 or 5 rays because we can afford it here. And let's say one ray tells us, or 3 of them tell us we are inside, but one doesn't. It's falsely outside. Okay. But since we follow the majority, we will classify this element as inside. We do this for all these, what I called boundary cells inside one group. Okay. So for instance, this one will be classified inside, this one inside, inside, inside. But for some reason, because we might have very bad geometry here, this one is classified as outside. Therefore, we do another majority vote on group level, saying since we have 4 inside, 1 outside, that means the entire group must be inside. So this one is basically overruled and also classified as inside. Okay. Any questions?
I think you should make questions
I should say questions.
See if they understood. I mean, you made me a particular class of this, so I understand it, but
So, do you understand why we do the clipping first?
And then search in a small set.
So this is the idea, the algorithm structure is basically the first thing we do is we clip. And all other operations, they just work locally on this like very small clip section. Okay. And so the three main ideas are find the group the cells, perform ray tracing only locally, not on the global model, and then combine as much information as you have, classify all as a whole, and do majority work.
Why to find the cut sets, you don't use the not span? Like the fact that I don't know, sorry, I got no, sorry.
So yeah, so the cut we need, first of all, we need to know them anyways, because we need to know which ones are cut. And here in this case, they serve as the boundary between inside and outside for the plot.
can you allow me to say, what is telling is not specific of IGA.
No.
So you can use it with a low order mesh if you like. It still makes a lot of sense. So this, I mean, it could be even, it could be even a not 3 mesh theoretically. So it would be more difficult in majority working. Actually, that's one of the important things, because this means you can use it, for example, in a standard CAD/CAM workflow. Okay, sorry.
No, it's a good point.
The standard campaign, I don't think it's as optimal as doing what we do right now, because you need to grow like navigating sort of the graph of the mesh, in this case, the node span. So then you have 30 million elements mesh, navigating this to fill the neighbors, it's super expensive. But if you have a node span, which is in principle much more reduced to the equivalent. So I think this is really suitable for this, much better than what we do right now, the standard ray casting. Well, not the standard, but the tuned one we have. But for the standard finite element case, I don't think it can compete to what we do.
So
I don't understand why.
So he's feeling like a parallel resistance.
But this is a very fast algorithm. It's called, this is a breadth first search is the coloring. This flight.
But you start from one point.
I'll partition it first. So
First in colors, yes, the blue.
The green and blue one.
So
Right.
coloring in, so giving colors to areas which are connected is very cheap. So once you have the graph, okay, that's a graph operation. That is very cheap. It's a breadth first search. And then what it does is that it selects a selected few. Sorry.
yeah,
No, once you have the gray ones, it's super fast.
Yeah, but the point
Don't
is,
look at ray casting. This is super fast. No, once you have the gray one, you throw the rays from the grays to the neighboring
to the neighbor, and I just look at orientation of the.
so the grays is very fast.
The grays is fast.
Yes, I mean,
Then I was wrong.
the
I
thing,
thought
the thing, the thing that needs to be fast is to tell what is the connectivity graph of the faces.
Yeah.
But once you have that, the algorithm is, and we have it in graph to set that algorithm.
I'm also partitioning the problem. I run, let's say, a flat fill only on this area, on this one, and this one, and then I merge them.
Sorry.
I mean, usually it's a sequential algorithm, the original version. Right.
Okay, parallelizing that, that's parallelizing a breadth first may not be easy.
So what I'm doing is I like have stripes. I fill this one individually. I fill this one, then this one, and then I merge.
Okay, that's.
Right, that's what we did with the effect.
I have a picture, but in the paper there's a picture. I don't have it here. But how it's. Yeah.
It doesn't have any problem if you have like thin parts of a volume that do not intersect in the local group. Like maybe I can.
Oh, yeah, just go.
Something like a people would slide, something like that. And it happens that a local group is divided like this, and you try to make something like this. So this will be classified as output, which is correct. But all of these inside should be classified. So as input, like inside, 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 inside. So how does it deal with this situation?
So they are cut. This wouldn't be inside.
Well, that should not be inside.
That's cut.
Yes.
So cut would, cut was part of inside.
Okay.
So this would be like the blue one.
Okay, but when you do the the voting of this area, shouldn't be classified as outside.
Ah, yeah. Okay. No, I get your point. Because I checked the orientation of the
Okay.
the normal.
Okay.
Yeah. Okay. Because this was exactly this example. So the original version from Benjamin, he said, well, we don't need to classify it all. We start with a cell where we know its color. So we start outside. So he said, let's just start here in the corner, flat this one. Then we know we are outside. And the rest must be inside. But exactly this you won't catch.
Yeah. Okay, yeah, but
But what he ensures, so you can have multiple colors, let's say, maybe it could be green, yellow, and his voting is telling that the things that he colors in yellow, they are all either inside or outside. That's what you're deciding.
Yeah.
Yeah, in yellow, if you have another group.
Yeah. So I mean, obviously it's recursive. Until all are visited. So the next one you would start here, for instance. Keep going.
So in essence, the first thing is that it finds the connected components, which are separated by its blue areas. And then for every connected component, it does a majority vote. So that's you decide what is more likely, that is inside or outside. I think it's very robust.
But my current assumption is each box is an axis aligned box. So it's not made for TEDs, it's just made for axis aligned boxes. It could be extended, but the current implementation just box. Yeah. Okay, so I also tested the robustness of the classification. Therefore, I took again the same 5,000 STLs, but I intentionally introduced flaws. Okay. So 1% of all triangles in all models, or every 100th triangle to say, is either deleted, flipped, such that the orientation is false, or passed twice, so that we have an overlap. Now, when we use standard ray tracing, and I actually shoot 5 rays per each individual cell. Okay. So this example, I would individually classify this element. I shoot 1, 2, 3, 4, 5 rays in the arbitrary direction, and I do a local majority. These lines, each line is one model, and the height is the number of misclassified elements. So the reference is the one I got with the valid model. So when you see that most of them have at least one misclassified element, some up to 5. But when you do the grouping, you can ensure that even with like these measures, you still get the same like labeling. But as I said, this just classifies. I just compared the elements inside and outside. They're still the same. You have obviously you do local errors at the cut ones. Yes, you will make an integration error at the cut ones, but you still can get a simulation model that's solvable. Then let's look at efficiency. Here I did not compute all 5,000, but exactly these, I think it's 11 models. And here's some numbers. So for instance, I think this is the largest one, which has 350,000 triangles. I think it's, yeah, it's this one. So you see with 350,000 triangles, you can already have very complex geometries with a lot of features. Then what I did is I put them again into a background mesh, and I measured the simulation time spent on each individual task. Okay, so first, how much time do we need for classification? How much time for the getting the intersection of the trimmed elements, moment fitting, and then from total would be input STL, output partial point. And it's done. I did this on my workstation. It's actually quite a good one, but it's not a cluster or like supercomputer in just a local workstation. And when we start with the classification, so on the x-axis we have the number of elements in the background mesh. But number of elements is now all elements, not only the active ones. So this also contains the ones that are finally classified as outside, but you still need to classify them. And this is why here we scale linearly with the number of elements, because we have to classify all elements. But for instance, the intersection of the moment fitting is only applied to the trim points, which is a very small set of all elements. This is why this is actually sublinear and cheaper than the classification. And then this is total. And see that we can get like around 10 million background elements in, not saying in all examples you will get 10 seconds, but just to give you an order of magnitude. It's usually faster than solving the problem, even for a classical static case. And then you can do whatever you want with this. So here in this case, I just applied boundary conditions with penalty method. And a self-weight that you can also apply extra Neumann boundary condition, whatever.
Now, I should ask you how you decide where to apply boundary conditions.
I will come to that. I mean, how I actually enforce them here.
Yeah, not how you do the penalty, but
Yeah.
how you geometrical.
Yeah.
You provide information.
Mm-hmm. Come to that. And you can get, I mean, this one is optimal conversions, which actually follows too, but I mean, in some cases, for these complex ones, you need to be very fine to get actually to your real conversions, right? But I think it's looking good. But now we can also run direct analysis of plot geometries. So again, I introduced these flaws for all 4 models. And here you have a comparison of the strain energy for H refinement for all 4 models. The solid line is the valid model. So no flaws would be the reference solution. And then the first one is 0.1% triangles are manipulated, and this one is 0.2% triangles manipulated. And obviously, for very coarse one, you get some errors, but essentially you converge to the roughly same result. What's actually a nice feature is that we can tell where we have a flaw in our geometry. Even if you don't see it, we can actually measure the quality of each element. And how we're doing is the following. So just imagine we have a small gap here. Right? So that means we could still apply the divergent theorem. We could still integrate over the boundary. We get a small error, which we can accept. But we can quantify that error. And we're doing this with, again, the divergent theorem. I told you that we can use compute the volume in this direction, or we can also compute in that direction. Okay. So essentially, both directions should give us pretty much the same result. Now let's say we have no flaw on this side and we have no flaw on that side. But when we have a flaw here, you get like this flaw. So the x component is now unequal to the y component. We can compare the two, and this pretty much tells us, okay, there is a problem. And you can define like a threshold. If this number is larger than something, you basically discard the element. Say, okay, I'm not sure what's going on there. Does this make sense? I mean, there are not only these measures, there's actually another one, because when you evaluate the weighted sum of all normals and it's closed, it should be 0. Because you have the same number of normals going this way than this way. And technically, I mean, I haven't done this, but technically you could even like visualize, okay, this one is something weird here. Okay, so this was the first part. Any comments? Then let's come to the piece of software where I actually implemented all this. This is quadrature for embedded solids. And yes, I'm aware of what eso means in Spanish. It was called differently before, but I don't want to go into details. We renamed into this. That's all I want to say. And
actually, this is being recorded, so this we will not share. Sorry.
Ah, yeah, okay.
We'll have to tell. Sorry.
Yeah. So it's actually a standalone GitHub repository, because when I started, I still relied on an external library to do all the geometrical operation, and the license was not compatible with Kratos. So this is why it's still here. But now I got rid of all the third-party dependencies, and it has now the same license as Kratos. And I already talked to Ricardo that we could eventually like more and more migrate into the, in some way, or get linked to it, or I think we will discuss that. But if you want, you can give me a star. Okay.
You'll have a star.
You already started. Yeah, I would have told you. Okay, so we have an input deck. I will come to this later, but what it does is it just takes the STL and it gives you this and it gives you that. I just have a very simple test case. So obviously this is for Kratos, this is for Kratos. So these are the main files you need to set up the problem. And here you have your geometries in the data folder. Now let's look at the GECKO parameters.json. this is, yeah, this is everything you need, for instance, for this steering knuckle problem I showed before. Okay. The first part are general settings. You just have an input file name, which is the STL. So that one is in here, and you just say that's the actual geometry. Then you have some mesh settings. So lower bound of x, y, z is just the extreme points of your bounding box. So you would just specify like this point and this point, and then it would create the bounding box. You can also say what are your dimensions of your parametric space. In IGA, let's say we use B-splines as background elements. Then there's actually another one called B-spline mesh equal true, whatever. But in that case, you could have a different parametric space. So the parametric space does not necessarily need to be similar to the physical space. You know, obviously it's just zero. Often it's just 0 to 1 in the parametric space. But it also makes sense in our case to make them just the same. But you can specify it here. Okay. You can also say B-spline mesh is false. Then it would just consider them as normal elements. And then your lower bound in the parametric space is on element level. So you would say probably -1, -1, -1, 1, 1, 1 to have your Gaussian space for the element. Then you can define a polynomial degree in each direction and a number of elements in each direction. Then there's a setting trimmed quadrature rules. The first one is the moment fitting residual. So when you do the point elimination, which is the residual you accept, which is, I don't know, 10 to the -8 or 10 to the -10, stuff like that. And then there's a min element volume ratio. So let's say when you have very small elements, they can actually make problems. With this ratio, it basically tells when your element is cut very small. So if you have something like this, and now this volume compared to this volume is smaller than this number, it won't consider it. But you can also set it to 0, and then you would get all elements. Yeah. Then there's a setting for the non-trimmed elements, for the integration of the non-trimmed elements. Default is just full Gauss quadrature, but here you now have the options of these generalized Gaussian particles, which I introduced yesterday. So this was, it does the decomposition into these subdomains, and then it applies like the local tensor product these quadratures. And as a reduced Gauss, obviously simple, and generalized optimal, reduced 1 and reduced 2. Now let's have a look at the conditions. So we have, for instance, in this case, 4 conditions. And each condition has as well an input file name, which is just the section of that surface where you apply boundary conditions. So I usually go to whatever FreeCAD or Rhino or the CAD system of your choice. You would just click on that geometry and usually as a function like extract surface, and then you export an STL for that surface. And you specify it here. You say, okay, since the surface load condition, we have a modulus and we have a direction, and then it applies force there. There's an interface for the Neumann conditions for surface load and pressure load. So pressure would be just in normal direction. And for the Dirichlet, I have an interface to read these penalty implementation and Lagrange multiplier implementation. We could also add the Nietzsche. I'm not sure if it makes sense in this case, but.
So I have a question for you guys. why cannot we use in this case the way of applying the clay condition we were describing before? The answer is because it cuts through the elements, right? So you don't have. First of all, even if this IGA wouldn't have the delta chronicle, so even there it would not be applicable. And also it is now in the middle of the element. Right? You need now you do need a weak position. You cannot do it strongly. Sorry for interrupting, yeah, but this is something a question that was made before about the weak position. And now here we do need the weak position. Or well, the Lagrange maybe is not pretty weak, but okay, sorry.
Yeah, so you can only strongly enforce the Dirichlet condition here, because
Yes.
these are the degrees of freedom are here. But you want to enforce so this boundary should be 0. This is why you need the weak. Okay, so then when we have defined this input deck, we will just execute the GECKO main. Just looks like this. So you put the JSON here and you say run. Okay. By the way, it's also similar. It's pretty much an application like any other application in Kratos. So like if you look at a structure, it will look very familiar when you know Kratos. So it's also written in C++ and has these pipelines to have a interface. When you execute that file, you get the output, which in this case looks like this. Okay. You have the elements VDK and the inversion point VDK. You can just visualize it in PowerView. You have as a geometry VDK, but that's just the input geometries. And you have 4 different STLs for the boundary conditions. Because what it does with the boundary conditions is the following. It takes this one as input, and you get this one. And you see that you have these straight lines here. Any ideas why we have these straight lines now?
But they keep line.
Yeah. So these are the element boundaries. Okay. Problem is you have an element. This is the background element, and you have a triangle like this. Okay. So now usually your basis functions are piecewise polynomials. You need to evaluate them on this span. Now, when you integrate this triangle, you would take its integration point, which is here, and the weight more or less corresponds to the area of the triangle. But now this point is in this element. So all this area would go to this element. So what you actually want is want to have a parameterization like this. That it's clearly this area goes to this element, this area goes to this element. And this is what you get here. But you already see that these meshes can look very ugly. But since we only integrate over them, we don't care. We just take the integration point from there, and that's it.
This is very similar to what you need to do for the model. Sorry, that's out of scope discussion.
Okay, then points on Python level, you can also say get integration points, and it's literally just a list of points in the parametric space, x, y, z component can get the weight. And this is, for instance, what I pass to Kratos and all. So far, it's actually done on Python level, but passed through Python because it was the easiest to make it work. But I think it's worth to move it to C++ level at some point. So what you get, what GECKO ensures is that each string element has the same number of integration points as Gauss quadrature. Then there's some optimal quadrature rules for the interior elements that are full. Then all integration points have positive weights and they all located inside the actual geometry. So you don't have points here, which is also done. Then you can, for instance, also get the elements. These are no real elements. These are just containers. It's not like there's an actual element formulation in it. You look over the elements, you can get their dimensions. You can ask the element, are you trimmed? And you can get integration points that are in this particular element. Yeah, you can, for instance, also get the B-spline, the control points, and but as I said, IS has an interface to Kratos, which again is now on Python level. Obviously, when we want to run a simulation, we need the material properties and the structural materials. Here we just have a linear elastic material law, Young's modulus and Poisson. And we have the Kratos parameter chase, the classical input deck that we use in Kratos. Just want to focus on two, like modeler and the process. Because the modeler, there's a NURBS geometry modeler. So in this one, I basically pass the information about how many knot spans and how the background mesh looks like, and it will generate it for us. Okay, so it will basically do this. Because inside GECKO, this is just, there are no splines. I don't need splines there. Okay? We only need the splines for our actual finite elements for the solution. And this modeler creates the knot spans and the control points for this B-spline. So, and then there's also a, what's it called? VTK embedded geometry output process, which basically just helps us to bring the solutions that we have. I mean, we get our displacements here, right? Because we solved the problem on the background mesh. But we want to visualize the displacement at the boundary. So this process maps into the boundary, and it works for the nodal solution, but also for the, how do we call it? Gauss solutions, Gauss point solutions. For instance, stresses, you would just evaluate. And then you get a BK output. Very small introduction to the
about this about that process. I did something similar for the CAD stem. So maybe we should eventually try to merge them.
Yeah, okay.
Or at least the API or something of this sort. So you do your stuff with the API, I do my stuff with the CAD, but the API is or to try to recycle as much as possible.
Yeah, good. I actually have sometimes the problem, because usually I use a direct evaluation of the stresses. So I take this point, put it into the parametric space of the background mesh, and I evaluate the stress. The problem is when the boundary is exactly here, then sometimes this point is seen to be in this element, which is not active. So it would be, so I also use the extrapolation to the nodes. So you could also map the Gauss results here and then bring them back, which is more robust, but it actually depends on for the spline, it depends on the continuity. If you increase the continuity, you won't get the peaks. Now the question is, do you want to have the peaks, or are they just but it's a bit weird. You increase the order and you get less stresses. Just as a okay, then
But it was just referring to having the same.
I know. Yeah, I know. Just came to my mind. Then very brief introduction to the C++ level. So I have a class called triangle mesh, which is essentially just a label of triangle. That's all it is. You read the STL file, and then there's a class called vref operator, and this contains all important functions. For instance, what you do is you say vref operator get trimmed domain. Okay. Then this point is this one, and this point is that one. So as I said, it's always an axis-aligned bounding box that you just define by 2 points. So all functions defined in vref operator just take 2 points. The lower one and the upper one. And you pass some. In this case, it's this min volume ratio I explained here, and the minimum number of triangles. So if it's just one triangle, it would try to refine it to get this minimum number of triangles in the mesh. Then you, for instance, from the trim domain owns the clip section and the intersection. So you can ask it, give me the triangle mesh of this one, or give me the triangle mesh of that one.
So just to be sure, I mean, I think I understand, but so we could, if we have our own mesh in Kratom, and that's a mesh of what? Well, of X's. For that mesh, we could give this to his library, and he will give us back the points. So,
yeah. Because then you, in the next step, in the layout right now, it looks like this, but I have to give it to an element just because that's how it is. But so I have an element class, which is just essentially a container. I pass the dimensions of the element, and it also needs to know its parametric space of the element. Because when I construct the quadrature point, I need to know what's the parametric space.
that would be a queso element, right?
That's just a queso element.
It's in the namespace queso.
Yeah. So yeah. Namespace is queso column. Yeah. And then you have the quadrature trimmed element assembly integration points. And this does the moment fitting and the point elimination and everything. And then, which are then stored again inside the element, again, which is just a container. And from there you call get integration points, which is just a vector of STD array 4. Like you have X, Y, Z, weight.
And it will also choose what is inside and what is outside. Here.
I mean, this one has the
name trace.
Yeah. So the distribution, because I think I haven't talked about the distribution of the points. So so we read the triangle mesh, which is owned by the vref operator. Then we call get trim domain. This will give us this section. Then in here, we first distribute the points like this. Again, here we need to apply local ray tracing to know if that point is inside or outside, right? Because we don't want to have points here. And then we do moment fitting and point elimination, and we end up with that point, those points. And and I actually distribute them with an octree. Okay, so what time is it? I love that. And by the way, these are the two publications which contain almost everything I discussed yesterday and today. So this one is mainly yesterday, and this one is mainly today, which has all the geometrical operations. I do have one more, I don't know, probably just 5 minutes, what I'm currently doing, but it's just not really related, just as an, it's called inspiration to what we can do for such a thing. Oh, any questions? So, since I work at the chair of Professor Bletzinger, and his favorite topic is shape optimization, and especially node-based shape optimization, I thought, well, at some point else I need to do shape optimization to make him happy. And now we combined shape optimization with this embedding approach. Yeah. So the idea is that we have an initial design, which is STL. We embed that geometry, so we say here's a run. Okay. We get the integration points, and then we give it to Pratos to solve the primal solution. We just essentially solve a structural problem. And then we need a step called sensitivity analysis. So what we are interested in, for instance, at this point, what's the influence of this point on, let's say, our objective, which might be strain energy. So what's the derivative of the strain energy with respect to the position of this point? And then we get the gradients here. And with this gradients, we can have a gradient-based optimization, which, for instance, a projected gradient algorithm, or it's unconstrained. In this case, it's a steepest descent. Essentially, you move in the direction of these gradients to find your optimal shape when you, for instance, want to minimize the strain energy. Yeah, and then we update the geometry, and we feed it back to the embedder. Okay, so doing this operation, the background mesh is fixed. It's always this, but the initial geometry might be this one, but the final geometry might be this one. Okay, it just moves through that structure, through that background mesh. And why we're doing this is because when you have large shape updates and you solve this with a boundary fitted mesh, and you start, so this is the initial geometry. You have a boundary fitted mesh, and your final geometry might be something like this. You end up with horribly distorted elements. At some point, you will cannot solve the simulation anymore, and you essentially crash. But whereas in this case, we always have a perfect discretization. And I don't want to talk too much about it, but this one are, for instance, the sensitivity analysis. So these are the gradients for the strain energy, the cantilever. So it's supported here. We have a loading here. And you can think of this, well, the maximum stresses obviously should be here. So here we have the highest gradients. That means what the algorithm will do, it will push, it may make it larger here at the support, which is, yes, quite intuitive. But the tricky part was to get these sensitivities independent of the background mesh. So now we found some formulation that we get, for instance, the same result when we have a background mesh like this as when we rotate it. So it's not independent of where the element is cut. And with this, for instance, is one example of a book. We can also apply design space constraints, so it shouldn't move outside of this, or these are usually called the packaging constraint. And this is, for instance, the final result. And with this now, so here you have the reduction of the objective, which is strain energy. So we make it stiffer, and the strain energy gets minimized. We have a stiffer structure. And at some point, you have a high reduction, high gradient in the beginning, and then it kind of becomes flat. Because at some point, your objective tells you you should go this way, but your constraint tells you you should go the opposite way. And then they cancel out, so you found basically the local minimum. But without this embedding approach, with the boundary fitted, you usually never reach this plateau, so to say, for solid geometries. You usually, I don't know, at this point your mesh is too distorted, and you need to at least remesh the model. And this essentially shows you the strain energy under H refinement, and just shows that we have very good discretization for the initial and for the final geometry. Oops. And this is another example. You might know this. What was it? GE jet engine bracket challenge, something. So the challenge was, it was actually a topology optimization. So we had they gave this box and said to the community, give us some nice ideas. And this was actually the design of the second place, I think, something like this, whatever. But we use this as our initial geometry. We have 4 different load cases. And in this case, the objective was to reduce mass and keep the strain energy, the stiffness for all load cases the same. And yeah, this is the result. You get some changes. And so here, you kind of converge to the result. You keep the constraints, and you have a, yeah, let's say converged discretization in all iterations. And now, let's see this again. Thank you, was very good. And this optimization is in collaboration with Riesa, which some of you might know. Give credit to him.
So when are you defending?
We'll see.
No, doesn't have anything. So
I would say in September. Well, at first I should say.
but that's normally takes 50% of the time to do 90% of the work, and there are remaining 50 from the 10% that remains. Anyway, let's go to it. It was very good. Stop this for now. We will not share it. I'm sure this will not be good.
Well, we are playing 25 minutes, but I think we can start. So basically, this is the handwritten tutorials of the isogeometric structural analysis and design. Part 1, we will deal with the geometrical descriptions, and we will do it together. So, well, so let's see what we will have here. So the first question is that, so we need to draw the basis functions. Anyway, for the given polynomialities and control point.
just,
Ah, right. So, okay. This. All right. So the next thing about the curve equals to 1. And in this case, we have a linear basis function. So I can imagine I would say this is the visualization of that. So I can go something like this. Which is the first, I would say, the first curve, second curve, and the third one. I think should be, we are familiar with you guys. And in physical space, instead of having points, we will have this line. Oops.
This case, as it's C0, you're interpolating all the points.
Okay, good point. So which one is zero?
The second one.
Second one. Right. And how about the first one? If the second one is C0, what
C
about
finite.
C minus one.
C minus 1? Because it's like three. So you have one. Then and go to the next page. Here for the quadratic basis functions, we have uh, these graphs, something like this, for example, and this one. Yeah, this is what we have for I would say p equals to 2. And if we go to the physical space, it's something like this. So this is it's not open non-factor, so wait a second. Something like this, I would say. In this case, I would say, yeah, we can subtract. I would say we have continuity C1. Yes. Yes. Sorry. So the first one, by the way, I forgot to mention, it is the case of I would say, so you see here dot 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 0, 1, 2, 3, 4, 5, 6 dot dot dot. Well, this is the case of well, I would say you know the what's the terms open not factor, but this is not that one. This is not open not factor. This is, I would say, we start with dot dot dot. So that's why for example, you go to this polynomial means 2, we start from that point, not from. You will see the difference between this one and the next step with open not factor. Then we have the fourth case for cubic basis function. We can do the same thing, but so yeah, I would say something. Just basically the splines and counter space for cubic. And here this is a bit tricky for the physical space. I have some. If you ask me what's the difference between the third and the second, I would say the third one, because we have higher polynomial degree. This is further away from the control point. I mean this one, but if you see the gap between this and that one, the gap is higher in the I would say in the case of polynomial degree equals to 3. So that's about the first case A, and we go to the case B. Well, I would say most of you know about this term, open knock factor. Now, I have questions on what makes it special, this open knock factor. What makes it special? I mean, why we use this open knock factor?
Interpolating the first, the last node from the point.
So if you see this example with the quadratic basis functions p equals to 2, we will have here we start from here and then this. And yeah, as mentioned by Juan, this is interpolating at the beginning and at the end. So yes, but you can see they have a kind of tangent here to the point, to the at the beginning and at the end. Okay, now, well, for the cubic case, we do the same thing. So it starts at the end, at the beginning and at the end, and then, well, it's same thing like before. We do something like this one, but if you compare again the gap, maybe this one versus that one, you see on previous example, further away from the control points. So, then, then the last part, well, the task is that to show the hierarchy of positions of the basis functions people to starting with constants basis. So, well, can start with constant. So this is constant. That's one. What I think. This. Okay, so it is easy. All right. Let's start with constant. So the constant we will have this here. Here and then by combining two constants basis functions, we obtain a linear basis functions. For example, the combinations of you see the left one and the middle one, we will have the linear functions like this. This is the I would say what I meant back then by hierarchy compositions. And of course, we can do the same thing. By linear basis functions, then we will get a quadratic, obviously. So at the end, so what I would say this is just the repetitions of the explanations from Professor Buchner yesterday. But yeah, I think most of you should know this already, so that's why I very quick in this first part with the basis functions. But now things will get more interesting yeah for the next step. So far, you have some questions for the for some tasks.
You try to do the dotted lines in the center.
Sorry.
What did you try to do with the dotted line in the center?
I'm just showing that this is a quadratic basis function, and this is well just let's say this is I would say there are both.
Yeah, but there are two lines. Please, maybe. Right.
This one. Ah, okay. You know this one.
Yeah.
So, I'm just trying to show that we have the same thing here. Quadratic. Also quadratic. Also quadratic shape. Yes. All right. So for the next questions, I would say we have this considering this following curve. Well, as you can see, figure 7, the curve with polynomial degree equals to 4. The first question is kind of an intuitive questions. Which polynomial degree must the curve have at least? Yeah, obviously this is the polynomial degree equals to 4, as stated from the figure, but that's not the, I would say, the purpose of this question. The purpose is just the intuitions. So we forget these terms, these explanations.
The quadratic as well.
Yeah, if you see the curve like that, so it must be at least quadratic, but why? That's right. At least quadratic, but why? Do you have some reason?
C0 will be just the point. C1 will be lines, and as here it's curved, it should be at least.
At least, yes. Then questions B. Well, we go back again to this we have to this curve. Well, now okay, we start with this curve with polynomial degree p equals to 4, and we want to set up the possible knot factor. This is, I would say, one of the most important equations that we must, I would say, know. If we are talking about B-spline functions, the equation of m equals to n plus p plus 1. I would say n is the number of nodes in the knot factor, n is the number of control points, and p is polynomial degree. Okay, so what do we know? So we know that here p equals to 4 indeed, right? This is stated here. And then what is n? Number of control points. So exactly this is first
8.
Yeah. Okay, 8. Okay. Then n equals to 8. So m 8 plus 4 plus 1 equals to 13. And well, here anyone want to try? Please the open knot factor. What is the open knot factor in this case? We have, I would say, so we have 13 entries in this case.
You should start with 5, 0.
Yeah. 5 points and
Okay, 4 zeros. And then, well, let's say, 4, 4, 4. Oh, sorry, let's make it 1. Make it easy. 1, 1, 1, 1, 1. Yes, and then we still have, I would say 3 entries left.
Be 1/3.
1/3, for example, yes. 2/3, sorry. B. Was should be 1/4.
1/4.
1/4. Yes. All right. Then the next questions we need to distinguish between nerves and these splines and visual. All right. So I'll make it also interactive. What do you think about, let's do it randomly, that get the blue one. What is that one? B-spline, nerves or visual.
Seems a B-spline.
Okay, we'll get this up. And how about this orange one?
That may be a nerves.
And yes, obviously the green one. Have easier though. Right. Now, why the first one is B-spline? I mean the blue one. Okay, so let me replace it. So we start with easier to make it more, I would say step by step. Make it more step. I would say to make it step by step, we start with this easier, this one. Why this one is easier? What are the properties of easier?
You don't have knots.
Okay, and right, that's true. It's and then what else? What can you see here as well? This, for example, in this particular example.
I mean, obviously there you cannot have local control in this.
Yeah, exactly. So I would say it's like
It's
if
a
you
50-degree difference here, so it's too far away from the control points because it's 50-degree.
so in my I would say both of you are correct. Let me replace it. So why this is easier? I can say that because the influence of the control points is scattered around the curve. That's how I replace them.
quadratic Bezier has three points.
So in Bezier curve, let me correct it. So p equals n minus 1. So this is the formula of Bezier curve. So in this case, you can see that we have 7 points. So n equals to 7. So it means that p equals to 6. 6. So yeah, to summarize it, I mean, in linear curve, if you have higher polynomial degree, it will, I would say, it's more distance to the control points. So that's about the first one, I would say, the Bezier. And all right, now that's clear that the others are either this type of or nerves. And I would like to ask you about the difference between those two guys, the B-splines and the nerves. Why we can say
The
that?
curves, you can see the influence, the weights, because for example, the curves is more close to the fifth point than maybe to the seventh.
Exactly, this one, right? And this, the difference between nerves and B-splines, yes, you're right. This is, you can see it's kind of shifted towards the points, and it's because of the weight. If you play around with the weight, then you can see that, okay, we would say that's the difference. I mean, B-spline is, I would say, special case of nerves where the weights are 1. So,
Not necessarily one, but all equal.
all equal. Thanks. Okay. So questions for the second part. So let's go to the third. Okay. For the third part, I would say we have these simple cases of nerves with polynomial degree 2 with the not factor, this guy. So simple, how many control points in this case? 1. So again, I will write this guy again. N equals to n plus p plus 1 equals to this case. 7 means that n equals to 4. Well, anyway, you can see that below we have 4 basis functions, n1, n2, n3, n4. Okay, so to draw these shape functions, it means that we need to have 4 shape functions, 4 basis functions. And well, first look at the first that one. I will use the red color. So from 0 to 1/2, let's say this is 1/2. We'll make a line here. positive something, I would say from 1 half to. And then from 0 to 1 half, we start with 1, obviously. We can put c equals to 0, and if we put c equals to 1/2, should be here, and since it's quadratic, this should be something like this one. Um, Right. For N2, you can see that we have two different parts of the curve from 0 to 1/2 and 1/2 to 1. And you can see that this curve is continuous, I would say, at c equals to 1/2, and well, I think most of you know what should it looks like, something like this. Two, and the rest, I would say this is a symmetric, so um, question B, we choose the valid control points of this one. I think this is straightforward. We have four basis functions, then we should have four control points. So this is self-explanatory. Fine. So this is, I would say, a simple exercise. How to determine, I would say, the positions of a certain, I would say, certain coordinate c at a certain point. For example, what is the position if I have c equals to 1.5 in the physical space? This one. So let's do this again. Right. So what do we have here? So we have these equations. This is the those are the definition of control points. So about the physical space, where this is the summations of control points multiplied by the basis functions. So this x c here, and then for the y coordinate, as you can see, yeah, you just plug in the basis functions multiplied by the y coordinates. And we can do also the same thing for x. So let's see from the previous page the so goes to 0 to 1. Zero plus 2, 1 minus c squared times 1 plus minus can be different, let's see. And I can say that I have comments with this part. This is the shift between the physical space and particle space.
Really, in the case of the
Yes,
EGA application in Kratos, do you use external library to compute the shape functions, or it's directly in Kratos?
it's directly in Kratos. We have, I would say, functions to compute given this one, right? Basis functions, yes. So I will show it to you either tomorrow or on Friday. But that's a good question. I have some comments about that. So in Kratos, if you go to the NURBS books from Google, and that the NURBS book, I think there's a certain algorithm, right? The recursive algorithm, how to compute or to, I mean, the algorithm of the basis functions. Yeah. But, we do it in different methods, which I will show it for you. Right. For the last task, no, actually not the last task. So these tasks we see, we need to draw a curve and show which range the control points influence the curve. And what does it mean? That so we have the influence of the first basis functions, we have the influence of the second, third, and the fourth basis function. So let's go back here to this one. So you see that this is our case. With the not factor 0.5111. So I can say that something like here. This is so this is the position C equals to 1/2. So this is our part, and this is where goes to 0. And this one. C. So from the previous sections, I think we are agreed that the curve have the shape like this for them. For example, this is what we have already discussed from the previous sections. Now let's see the influence of each basis functions. So you see the first basis functions. I go back to the previous page. This one. It only has values where C at the range of between 0 and 1/2. So if I go back here, the influence of the first basic functions is only on that one. I mean, only that one. So it's not, I would say, it has no influence to the other part because of the reason that I have explained before. We can also say the same thing for the four basic functions and four. It only influence the other part of this curve. Right? And then for the second and third basis functions, you see that the influence should be for the entire curve because, yeah, as you can see here, this is by definition. So I draw these things. The full influence for the second and third basis. Then here, the last part, to draw qualitatively the curves of the corresponding shape functions. Well, I think we can start from the second part, this one, which is similar like before. Same thing. And now we have these cases. So this is 0.5 and this is 0.1. So what do you think about this, I would say, the curve in physical space if we have this kind of wavelengths? Well, these things, I repeat that this is the half point, c equals to 1/2. And this one, I can say the same thing here. This is the also point where we have c equals to 0.1. That point would say. So what I want to say qualitatively, we can check these points. This is the, we'll say 1.1. What if we have something like this, 0.0, let's say 0.8, 111, what this is, I would say the same thing, can we have this one, let's say, factor of c equals to 0.8, and also, this close to that point, and look at that. That about the, I would say the curve on, I would say the physical curve in physical space, and then now let's check the left one part, basis functions. So let's do it step by step. Here on the last part, I would say with the not factor 0.5. This is clear. What's the equations? This is something that we discussed before. 0.5 again. I would like to do the same thing here with 0.1. So this is, I would say, um, and as you, I would say, you can already notice that, yeah, this is close to 4. So it's kind of shifted to 0.1, all of the curves. The fourth part, we will talk about the continuity of the functions, and now we can say that this one we have 0.5, 0.5. So let's do it like this. So n equals to n plus p plus 1, and in this case you can say that just 2, 3, 4, 5, 6, 7, 8, 9, 9 plus 2 plus we have 6 points here. Okay, so what I want to say is that there are two critical points that we need to check 0.5 and 0.75. Okay. Some of you are familiar with this. I would say these some simple I would say equations to check the continuity of the functions. So C we have P minus K. So for C equals to 0.5, for example.
C0.
C0, exactly. Because P equals to 2, K equals to 2, multiplicity, we have two 0.5s. So what is the meaning of C0? It's king, I would say. It's still continuous functions, but you can see this is
It interpolates.
So I would say this is where I would say if you're talking about the physical space, this is where it's located, 2.5, and I can expect something like this. This is a king. You can do the same thing to check C equals to 0.75. This is supposed to be C1. No, I would say this is not a king. I would say this is continuous, and 1 time differentiable. And last but not least, let's draw the basis functions. We'll do it very quick here. First, something. So, the next step is second curve. What's happening here? So we see that now we have 0.5.
Sorry, can you go a bit?
Yeah. So,
Can you explain why it was 0.5 is in this specific point?
this one. Um, well, that's good. That's, I would say,
You can see that the basis function n3 at c equals 0.5 is 1. So that means that when you multiply n3 by the control point number 3, it will be 1 for the control point 3, and all the other functions will be 0. So it will interpolate the third control point. Do you get what I mean?
Interpolate what point then?
The third point.
Okay.
You get it?
Yeah. I know it will be in some point, but why not?
And I write it really in this.
the logic. Yeah.
Ah. You have that x so when you evaluate this function in C equals 0.5, all the n will be 0, except for the third one. So this is 0, this is 0, this is 0. All are zeros at 0.5, except for n3. So you multiply n3 by the control point number 3. So it will be 1 by n3, by the control point 3. So you interpolate this point.
Right, now the second case, you have this 0.5 two times. So what will happen with these things? So okay, the critical points and 0.5. If we go to the continuity formulations, it means that we have c minus 1 or I would say this is discontinuity.
Sorry, for which vector?
This one, yeah, 0, 0, 0, 0.5, 3 times. 0.5, 0.5, 0. So yeah, in this case again, well, I repeat it again, we have discontinuity, and if we try to illustrate the basis function, we will have something like this. Two, three, four, five, six. Equals to n plus p.
Escape, Einstein.
Yes, it's frequent, exactly, frequent, it's back to Bernstein. So that's why on the next page you see these things. Would say you have, I would say this some type of not vector. This is a type of not vector. So yeah. All right. Then now the curve. So it's clear that we have discontinuity here. So I can go something like this. It's continuity. Yeah. If we have things. Third and fourth positions for this.
Can you go back just one page because I want to double check something?
Yes,
The previous one?
this one.
Last case where it's C minus 1,
Yes.
0.5, which are the values of N3 and N4 at that point?
At that point, I would say you cannot compute that value. So if you try by yourself by hand, it will be, I would say, almost infinite. You can
Okay, so it's enough.
yes. Considering the time, we only have 5 minutes before the break. But I would like to say I will skip the fifth part. I mean, we will do it after the break, but we jump after the sixth part, the final, because it will take less time rather than doing the fifth. So we will do the sixth part about the final, then we will have the break. So let's repeat the sixth part about the final. All right, so I think most of you know about the requirements. So the first things that we need to do is that, okay, let's do this step by step. We need to perform the, I would say the refinement in the first case is A. So easy. This one, as you know, this is P equals to 2. With the refinement to P equals to 2 means that we add more zeros. So we add one more. 5, 0.511. Forward, and in this case we have and equals to 10.
So let's say the goal is to raise the order, keeping the same continuity.
Exactly. That's the use of the refinement. So in that case, n equals to n minus 3 x1 equals to 6. For that, basically, I would say the original basis functions, it has more basis functions, and the new one it should when you see it should have 6 based on our based on the definitions of expands. So this is first one. I would like to use it about 1, 2, 3. In the next part, it's so yeah. So yeah, the next step we need to consider a case which the preservation continuity is not fulfilled, and we need to know a system where the information get lost. So you can refer to the to this original example here what we have with these things. You cannot factor 0.5111. And in that system, for example, we have something like this. I don't know, it depends on the positions of the control point, but we have this C0. For example, we have, let's say, this is something that we I would say desire. We have this desire king, C0 continuity. Let's say in this new system, I would say if the multiplicity is not Python, this what will happen. So we will have C1 continuous or C1 continuity, and this will violate it again. So this is if you are not doing the multiplicity. So I would say, let's say if we want to please up the king, we do it the other way around. So we want still have king.
In that case, you are not interpolating the control. So if you draw the same control point as before, where would be the curve?
Exactly. So in this case, I don't know, this something like this. This is the control point. That case, maybe something like this. But this is what you need. So that's the last part of this of this requirement. Well, the second actually the second part we will talk about not insertions. So in this case we have 0, 0, 0, 1, 1, 1. We do not insertions, so we will have these new not vectors. 0, 0, then 1, 1, 1, and in that case, into the 4. So we have 4 total points. Now, this is finally last time, before we take a break. So, I will put it, I will say I will, make it open. What do you think to answer these questions? Why we do, I would say, first, I would say, why we do, I would say, to carry out the refinement before we make refinement. Why we don't do the other way around. I think yesterday, yeah, Professor Luchna has already explained about that concept, but little bit parts
Because we can raise the continuity at the node.
because we can base the continuity at each node. Okay, that's if we are doing the K refine. We are doing the other way around, what we have. Let's do it. Maybe
If we press the section,
it's what the yes. We do first locking shelters, then the next step we do refine, refine. Okay,
we lose the point.
let's do it step by step.
We lose something, right?
Yes, we did something exactly.
I cannot say, I have it in my mind.
Yes, I think you almost get the answer, but I mean, you're trying to build the sample to answer to that. All right, let's do this. Let's say we start with this step. Usually, I would say this is what we have. We start with this electric B equals to and separately we can get it. So it means that we do P first before H. So that's P that we have. So, let's say we have two elements. So we have, let's say we do two H refinement. We do refinement now. So H refinement now. What we can see in this case, I mean, if you consider this part, that part, we can say that the continuity of this one, so we can say let's say something like this. Take refinement and we do the other way around. Let's do it the other way around. We do H refinement first. We will see what we will compare this. This is 0.0, 1. this case, at this point, I would say, can say that the funding case C1. Right, because we have B equals to 2 and A equals to 1. And then we do X refinement, sorry, P refinement. This is what we will get 0.0.0. The 1/3, 1.
You have two more control points.
Exactly. So I would say that if you okay, in this case, this is I would say equals to wait now
Where's the K defined?
which one?
You should take P refinement from P2 to P3, and you should erase the K refinement. should
So
make it a P.
yes. But yeah, that's so. So you can see the difference between the left part and the right part. What are the differences is the continuity. So you see that doing the K refinement and doing the other way around, you will lose the continuity. So that's
We lose 1 degree of, it
So-
will always be 1 degree of continuity.
that's basically I would say that's something that we want to say before, right? So yeah, basically that's so this is
And completely, what happens if you, in the second case, if you increase 1 degree, say from 2 to 3, but you don't add the 1/3 and the 2/3. Let's say you keep the multiplicity to 1, then you have the same continuity.
I give the multiplicity to 1 over the second.
Because let's say you are making the non-vector open, because you are adding 1, 0 and 1, 1, and at the same time you can keep the continuity to C2. Do you get what I mean?
So you mean that I only increase this one and one.
Yeah. What's the problem doing that?
I mean by the beginning of the refinement you increase all. Can say
Yeah, I would say it's computing the control point. I mean, every time you modify the, vector by H refinement or P refinement, you have formula to compute the new control points. If you do it with in a new way, like adding 1, 0 or 1, 1 at the end, I mean, without doing the complete refinement, you don't have the formula to compute the new.
Okay.
that's it. Thanks. That's by definition that's so yeah, in practice we go to this way. We do a refinement first, then we do exercise because with that we are sure that okay we want a certain level.
But sorry, it's in one, no?
One,
In
yeah,
one
A1.
value.
A1.
If it were a surface, we would have a one and a two.
Yes, exactly. So because we are talking about one dimensional, we only have yes, one, A1. So I would say if you go down, you can say that we have we need to compute I would say the x and y component. So yeah, that's yeah, you can say the example for the y component. We do the same thing. I would say I will skip some parts of the calculations, but basically this is the same line. It's like
So it's a sum of
I
MI,
see.
MI,
and I yeah times the control points. So this is what I mean. This is I. Let me say C times control points. Times control points. Yes.
What is the base vector subject?
Sorry.
What is the base vector?
Basically the derivative, the
Okay.
derivative of the I would say the curve,
So let's say the tangent vector to the curve.
the tangent vector of the curve. Yes.
We are using these basis functions.
Yes.
Because I think we have to skip the part, the page before.
Which one?
Yeah,
This is just, I would say, the previous page, just of the explanation. So we have this kind of curve, we have the control points, we have basic functions, blah blah blah. But I mean, you
One
can,
question.
Yeah.
Why is it a derivative, no? Of the
derivative, yes, this is the derivative
There's
of
a
data
missing, no? Or no? Isn't there a D missing, no?
There
There,
it's ny, comma, c.
comma C.
no, in the next line, X component of AI, A1.
Which one? This one.
The superscript and the subscript. The superscript is I, the subscript is 1X.
Sorry.
No, the superscript is one for batch I.
Done.
It's
Okay, I got what you mentioned.
I,
Yeah.
superscript, subscript 1X.
One x.
Okay, now I get it, I get it. This
For
is,
it's a curve. So just one base vector. And one at the top, and then it's because of batch
so, this is right, this one, I mean that one, right?
Sorry, I meant
Yeah.
that one, I meant that
Okay.
one. I mean, I didn't know.
That one.
Ricky, I have a question. In A1X subscript 1, the superscript 1 stands for patch 1.
Yes. This one, the superscript.
The superscript is patch 1.
Patch. This- You can put that things by yourself, but this is what you'll get at the end. just put, I would say, in the answer, because yeah, you can compute it by yourself, but just conclusions, I would say, yeah, do it very quick, because we still have the second part of the point that we will have outlined. So this is just, I would say, just to show you that, okay, this is the derivative of the basis functions. This case, let's say we compute the base vector, the x component and y component of the first and the second class. Okay. And all right, let's go to the point B to evaluate the base vectors at C 0.5 and 1. Let's do that. So first, curve point at C1 equals to 1 half. And now let's do these visualizations, I would say. So I would say this is what we is the A11 when C1 equals to 0. Here I can say this is A11 when C equals to 0.5. What is interesting is at that point we have also again the same thing, A11. So at C equals to 1. Same thing, the A12 for the second part. So yes, this guy, and that.
I think the X's are missing the subscript. Like, because you wrote, I think in the beginning, C1 equals to.
Yeah.
Yes, so yes.
So, okay, I think most of you should be done with that. So let's think about it. So what, I have questions. So what can you spot in at that point? This will answer, this is the answer of this point C. If we compare the base vector at those points, what kind of continuity here?
C1 continuity
Yes,
and G1.
and G1, exactly. So that's because here we can see the relationship of the first, the base vector of the first parts and the base vector of the second parts.
So it should be alpha or should be one.
Should be alpha, and if you put the number from the previous page, this is sorry, I will try to be very quick, but you can check by yourself after this. You will have this kind of relation. So alpha equals to 20 in this example. Alpha equals to this value, and this is the one continuity.
So to ensure a G1 continuity, we just need an alpha.
Yes,
Doesn't matter.
it doesn't matter. So what's the difference between G1 and C1?
So in C1, alpha is equal to 1. So the speed at both sides is the same.
That's why in this case we have, instead of C1, we have D1, because this value alpha. I mean, if you ask me one for the value, you can see the previous values. To be right there. At least in this example, we just want to distinguish this difference between C1 and D1. And then I would say the last question is just if we want to draw qualitative with the base vector. So let's consider this is the base vector 1. Let's let's do it like this. This is 1. This is 2. Then imagine something like this. Just say example.
Sorry, Ricky, which are the representative positions?
Right.
What do you mean by representative positions?
Well, this is just the qualitative. I would say whereas representative means random in this case. Well, yeah, it's something that we can draw on this on this. Now I think we gone through the first part of the exercise, and let's go to the second part. I think on the second part, we will do practical things. I don't know, I just want to ask you if you have any experience to I would say to compute this kind of task using IGA element. Okay, so let's like so considering this simple beam, also requires simple class model. So let's do it like this. So if this is a finite element model, we will have three elements, right? But no, but since we are talking about IDA, the element is not free. It depends on the knot factor. In this case, we have two elements. I mean the non-zero knot, and here we have this one and that one. So I would say we have two elements. And then also this is given the informations of the positions of the control points. First control point, second, third, and fourth control points. This is I would say so given by this given for this problem, and I would say this is quite similar like final problem. I think every of you should know about this simple set class equations. We have to solve that. Let's say that part is if we write the principle of virtual world, I don't think that we should spend more time on this. And this is the basis functions. I would say from the given knot factor.
It's two elements or three elements?
Two elements.
Two.
Two knot spans.
Two knot spans.
Two elements.
Okay, good.
Here. More you do this,
Okay, so X is control point. Right, so let's compute the analytical solutions of these examples. So the forces is F, simple. This is 100 kilonewton. If you go back from the previous page, and the well, I would say the normal stress would be 100 divided by 1. Just And here we just put the numbers of the numerical solutions. Then, well, you see that we have the constant forces, also constant mass, constant strain, and linear displacement. So, that will be to this, well, I would say one of the most important part, concept of isogeometry. So considering the first element from C, between 0 to 1 half, this is what I would say, the description of, in this case, this curve, I would say the, x, c, well, again, by definition, it's the summations of the basic functions multiplied by the control points. So you have, 4 control points, multiplied by, 4 basis functions. We just put this, let's say the, this is given from the previous, from this, first page, I would say. We just put, some things. This is, I would say, the positions of the control points.
But that's for the first element.
This is for the first element. Remember, this is between 0 and 1 half. And the end. if you look, I mean, if you look, would say video below, you can see that the basis functions here. I mean, for the first element, the only basis function which is relevant are n1, n2, and n3. Because n4, well, it's zero. And the concept of isogeometrics means that displacement and I would say, the geometric descriptions are just, we can do similar way by I would say, summations of, I would say, isoparametric concept is applied. Also the summation of the multiplications of basis functions times the, I would say, control displacement in this case. And we do the same thing here. Then if we compute the derivative, so good. Okay, the next step. We would like to also to compute this Jacobian. Well, the importance of Jacobian is simple. Of course, we need to do the mapping from physical to the parameter space and vice versa. And I would say we use also. I mean, we will use the chain rule here. This is quite straightforward. This is pretty much similar like what we have in the classical plan. Since this is just, I would say, one-dimensional problem, the denominator of Jacobian is Jacobian. So, we can factor form. Right. So far, do you have any questions on those? So far, we just compute, I would say, what we have done. What we only compute the mapping, and we compute the, I would say, the isoparametric, applying from isoparametric concept, we have the displacement functions, and now let's talk about the other stuff, the local stiffness matrix. So in this case, the task is to compute the stiffness matrix. Considering the fact that we have this virtual inner word with the test variable W2 and actual degrees of freedom D1. So I would say that this is pretty much similar to the fundamental. We can have the integral over the length from the let's say this is n2 comma x multiplied by the modulus multiplied by the x dx. And now you can see that we need the derivative of the basis of step functions with respect to x. That's why we need the mapping concept before the Jacobian and also the also the I would say the inverse of Jacobian. But now if we also can be defined by this a plus 1 multiplied by EA also a
We either have from C0 to C1, as it says. What did it say? From the integral, C0 to C1.
from C0 to C1, yes.
C, C, C.
Yes, I agree on that.
You are the master of that.
You should trust it.
Okay, so far we already computed the Jacobian, so the inverse of Jacobian, determinant Jacobian, also the the derivative of those are the basis functions. Then we have everything, we plug all together, then this is what we get. EA times 5 minus 8 not a logarithm 2.
you say J1 is like the same,
Inverse of
the inverse.
the inverse.
The second is the inverse. The first
Yes, first and the second, they are the inverse because here
is too close. Okay.
this is
Yeah, it makes sense to be the inverse.
the isoparametric concept.
No, it's just the right. Okay. Yeah, it's J minus 1. Okay.
Okay.
The first.
This is
Yeah, this was okay. The first is a little.
okay. So far, we have the integral. Now, what is the next step with the finite element? So we need to, I would say, to compute the integral. There are two different ways. First of all, we go to the next page. We have the analytical integrations, and of course, if you are writing your own code, usually we do the right hand. I would say on the right hand side, you can see this is the numerical integration. We usually do that numerical integrations, but what makes IGA special is that IGA has three domains: physical domain, parameter domain, and Gaussian domain. So the finite element, we only have, I would say, the physical domain. We map that with the Gaussian domain. But here in IGA, we have the parametric space. That's why we have two steps of mapping. Which I would say you can see from the picture here and also from the yesterday's lecture. So the next page is just how do we solve that when we compare how to solve it analytically versus to solve it numerically. So this is easy, right? For the first one, this is just well, this is I would say our analytical solution or that we will compare with the numerical equations. And yeah, just a quick question. All of you should be familiar with this, right? I mean, I would say these formulations. I mean, to I would say to compute the integral of a function's numerically. Right. So I would say because of the time constraints, I would say I can skip this part, but at the end, well, the integral can be defined as the summations of well, it depends on the number of those points. I think Manuel explains that this is, I mean, in this exercise we use the standard Gaussian quadrature. So I would say in this case we only have 2 points, and we put that into our functions. Then we need to weigh the I would say the determinant of Jacobian, which is our and at the end of the day, I would say the results should be comparable between the analytical and the I would say the numerical Gauss point integration.
In this case, as you're choosing a Gauss bound quadrature with two integrating points,
Exactly.
integrate exactly up to all the three.
Up to it. Next point we have here. So if I go back to the previous page, we can perform the integral in a physical domain. I mean, since we are in the IGA world, we have physical domain, parametric, and parametric domain. There are two different ways how to compute the integral. We can compute it in physical domain. For example, if we do it analytically, we do simple integral of functions over the x, but we can also do it numerically, which is show it to you before. And we can also do the analytical integrations in the parametric domain. So we do mapping here. So I know this is just a dummy oratory example, but this is just to show you 4 different ways how to do the integrations. We do the mapping and we compute the integral in parameter domain analytically. Of course, we can do that in numerical way as well. So the thing is that here we have to consider that if we do that, we do the, I would say, numerical integrations in parameter domain. We have to consider this two, I would say, we have two determinant Jacobians because I would say first we have the mapping from the physical to the parametric domain, and then here this step we have another mapping. I just want to, I would say, emphasize this part here. We have that this one, this guy is the mapping between physical and parameter domain. This one from the parameter domain to Gaussian domain. For take-home matrix or as a summary, in Quartos, for example, we do this one. This is what we do in Quartos. So we solve the integrations in the parametric domain with numerical.
We use normal quadrature rules like different Gaussian, or use reduce as well?
Well, we have both. I mean, on the exercise on Friday, I will show it to you that we have. I would say we can select the type of Gaussian. We can use normal one. We can use the, I would say, the other rules that have been explained by Manuel. But for more, I would say, at least in, I would say, normally we use the standard. So I would say again, well, this is, I would say, on the next page, you see the solution of those 4 different types. physical domain analytical integrations, physical domain those point integrations, parameter domain those integrations. I would like to skip that part because this is quite straightforward. At the end, we will get this. I would say we will have this. Let's say we convert to that value because we are still talking about one-dimensional case with polynomial degree 2, and we have enough gross points to solve this one. And, I would like to say that well, this is a good hand in writing exercise if you have time, but this is not the important part here that we would like to explain in this exercise. Now I think I want to go to questions app, so we can this question directly. Now this is related to global stiffness matrix. What is the difference between the global stiffness matrix in IGA versus general?
The bandwidth.
The bandwidth, exactly. In IGA, I would say the element stiffness matrix depends on the. Wait, I'm asking when we have 3 times 3 here.
Because there's a force p plus 1.
Exactly.
Quadratic basis functions. 3 control points.
3 control points, 3 times 2. Exactly. What I want to say is that if we change the polynomial degree, the size of the element stiffness matrix will also change. In a second, I will show it to you how we assemble those element stiffness matrix and global stiffness matrix. Right. Again, well, we start. I will start with these basis functions. So I will be different. So if you check the degrees of freedom in this example, we have so I would say so that this no, let me replace it. Here you can say you can see 4 control points, and you can see also 4 control variables. U1 hat, U2 hat, U3 hat, and U4 hat. So from this, yeah, in these examples, you can directly see that at the end of the day, your global stiffness matrix will have the size of 4 times 4 because we have 4 control points. And as you can see from the, I would say from the basis functions one, two, sorry, let me change the order to make it better. So let's say this is N2, this is, sorry, I put the wrong order, so N1, N2, and N4. For the first element, the CPs, the control points, which influence the elements are N1, N2, and N3. Because if you remember, this is the first element from 0 to 0.5. This is the, I would say, first element, and the second element is from 0.5 to 1. And if I see the basis functions, the first element is getting influenced by N1, N2, and second element, yeah, you can guess N2, N3, and so it means that this to assemble the global state cosmetics, the first, second, and third respective columns and rows are the part of the first element, and the second, third, and fourth column are the part of the second element. So questions, notes. Now, in 2D, how many elements do we have considering this, let's say this Knot vector? So I would say this is the first element, for example, this is the other elements, and so on. We have 4 elements in this case. And let's talk about the first element. Let's talk about the red element. This is the red one. So the same case, like in the case of 1D, in these 2D cases, in this 2D case, these are the control points which influence the, I would say, the first, I would say the red element. So you have the same concept of that about what we have discussed before in process. So now, in this case, we have 20 by 20 status matrix. This is also a global status matrix. And well, let's draw the first elements, the red element here into the figure, to this, I would say, to this configuration. So what do we have here? Simply this one. Can someone explain it why we have these configurations?
Because we will have one equation per test function. So for example, I don't know, when you are testing against the test function corresponding to the control point number 6, that corresponds to the set, to the set row, you will have all those degrees of freedom. 1, 2, 3, 4, 6, 7, 8, 9, 11, 12, 13, or 14.
Yeah.
And then the same with everything.
Same with the others. All right. So let's go to the last part of the exercise, well, the post processing. So, well, what do you think the difference in IGA and finite element compared to the post processing steps? Well, the finite element, after we solve the equation system, you will get the result, for example, the displacement. And this is also the direct result from the displacement because the fundamental is, I would say,
Now we have control points, and we have to transfer the displacement of control points to the nerves.
yeah, exactly, because basis functions of these lines is well, on the topology, so it means that this is the results at the control points, not at the, I would say. So if you want the displacement, the real displacement, I would say, what I'm
What about the control?
But in this case, the control points coincide with the geometry. In this specific case.
yes, that's a good thing. But we will see. Let's do this. This one I don't. We will do it. I will not do it because I would like to show you something. Something interesting things insane. At least in my opinion. So let's remember these formations again. This is the summations of again the basis functions times the points plus the space. The end we will have these displacement functions, which is also the we need that, for example, for the calculation of strain and stresses. Here I think we did that also before. So, I did not. One, what you will get is if you remember the exact solutions, then we get also the same one.
Can I say something?
Yes.
On Friday, we will see an example in Kratos, and in Kratos we know the value of this function only in the Gauss point, in the integration points. So in the post process, we will compute always the solution only in the Gauss point because we know the function. Because if we want to compute the solution in another point, we will need to calculate the basic function at that point and then do the summation this function at that point times the solution of our system. So yeah, except in this case, it's all we know the unitary version of the basic function, so we can recompute at the end in the post process the solution where we want.
Okay, thanks for the remark. Okay, let's continue. So here, did you realize that these functions, the displacement functions here, this is quadratic, right? Using c squared, but to go back to the, I would say, analytical solutions, this is linear. Right? Why does it happen? Higher the continuity, yes. And if I mean, this is, I would say, the displacement functions with respect to, I would say, to the parameter space. But if we do one more step, in this case, we try to have the displacement functions with respect to the physical positions, I mean, ux instead of u. We
Should be like
we obtain this ux linear.
So if in a practical problem, you want to know, for example, the stress at a very specific point, you need to know which are the parameters U, V, and W corresponding to that point, and then you can evaluate the basis functions at that point.
Exactly. So yeah, what I want to say, the method is that be careful with that. I mean, if you compute, for example, this one, displacement c equals to 0.5, that one, well, might be coincidence with the, I would say, the displacement of the real displacement in physical space.
so it's because you have two mappings, it's like linear times linear, yes, for this is the explanation, right?
No, the explanation is because the geometry is represented by quadratic basis functions. So you are combining linear displacement, quadratic geometric representation, so you get quadratic displacement.
I mean, for example, if I put, let's say, c equals to 0.25, this is what we will get, right? These points. We after we plot, I mean, in this case, we plot that that displacement and functions. But this one, the value that you get, u c equals to 0.5. This is not, I would say, not the real displacement that we are seeking, for example. In that case, you need to compute the displacement field ux using this, I would say, this extra step that I told you before, one more method.
So in order to get which is the parameter associated to that point, you have to solve the nonlinear problem in this case. To get which is the C parameter. You get it? If you want to go from the physical plates, let's say the inverse of the original transformation, you have to solve a nonlinear problem from the physical domain to the parameter.
Now, I would say I'm done with that. This is, I would say, the last part, post-processing to like Lane Lagrange strain and second pillar Kirchhoff stress. I would say this is some extra feature if we are talking about, I would say, this is the, I would say, the class elements that have been explained from yesterday. I will skip that part, but let's go back to these things. What will happen here? Okay, so let me rephrase my questions. Can we have a case where you see, I would say, equals to ux and purely coincident, so you see linear? Is it possible in this case?
What is the question?
So the question is that in this case, you see that we have, I would say, non-linear you see the displacement here. I would say the displacement with an environment of this one, this guy. And is it possible, for example, in a certain case that you have all the, I would say, linear C?
In the case you're using a linear transformation between C and X, you will always have, let's say, a different U0.
Yes, this one, right? Sorry, that one. Exactly. And what do you think about it? Yeah, exactly. It's possible. And if you go back to this example, you see these positions of the control points. We put it randomly. Right? We just divide it I would say, maybe equal distance. And at the end, because of that, we obtain the non-linear, I would say, how to say that, non-linear relationship between C and X. But you're right, there's a case that if we put these control points in a certain position, for example, so if you put your control points, you shift that, for example, I mean, you 1, sorry, 1/6. No. So this is 1. Yeah, this is. If you put your control points in this case like this, you'll have really linear relationships between X and C. This is also things that I would like to emphasize, because if you this is related with the if you check the notes book, that you remember that we do decay refinement. So we have let's say we start with 0.00111, for example. We start with that, and then we do, let's say we do K refinement. We have that one, this Bezier or Bernstein curve. Then we do K refinement on top of that. And if you check the algorithm how to do refinement, I mean in terms of, let's say this one, we have control points here and there. This is I'm talking control points, and if we do the refinement, let's say we insert one node, this is what we'll have, and if we insert more, this is what we have. So there's a certain positions of that point to maintain the linear relationship between C and X, parameter and physical space. So
I don't get it. How linear relationship? If you're using, for example, quadratic basis functions, you have a quadratic relationship between C and X. I don't get it.
Exactly, but at a certain position of control points, I mean, if you, I think I have if here this one, we have 0, 1, 2, 3, the control points in these examples. But at a certain, I would say, let's say this is x1, x2, x3, x4. This is one, this is 0, this is 5, this is, I don't know, what I want to say is that there is a certain control points, I mean, there is a particular control points where at the end you will have the relationship, I would say direct relationships, in this case, possibly. I mean, but I forget the number, I think.
Even when you are using higher order basis functions.
Yes.
So, for example, you're using cubic basis functions and you end up with a linear relationship between x and c.
Probably would be other points, like two, right? Would be other position.
Yeah.
Different position.
Different position, exactly. This is what I want to say. In practice, usually we don't, I would say, if you are using, I would say, the commercial software like Rhino, for example, it will automatically find, I would say, that linear relationship if you do refinement
So
in Rhino.
there is always some points for every order.
Exactly. So, I mean, in these handwritten examples, we do the toy examples, we put the control points randomly. But if you go to the CAD software, they will use the linear relationship.
So in that case, you don't need a point inversion algorithm.
You don't need a point in.
So given a certain point in the physical space, there's a linear relationship with the parametric space in those specific points.
If you put them in this specific position, you end up with a linear, right?
So at the end of the day, what I want to say is that so we have x1, x2, x3, and x1, 0, 1, 2, and 3. By the way, this is just some extra stuff. It's not included in the tutorials. Just I would say something that I would like to share to you guys. This and parameters is from 0 to 1. So what will happen, for example, if I put c equals to 0 here, in this, I would say in this function, for example. So we have x equals to 0, so this will map to that point, right? And this also will do the same thing. But in this case, what will happen if I put, well, c equals to 1 dot, for example, is if equal to 1? No, not right in these examples, because 4 times 1 third times 2 third square not equal to 1. Right. But what if we put c equals to 1/4? Let's do it like that. 4 divided by 4 is 2 divided by 16 over 10. trying to say is that this one. So you have we at a certain points it's I think this is something that I need to check. I don't remember very hard. We have this kind of this control points, and you put this back here. Of course, this will change, right? You have new C and X close to something. And if you put, for example, this is this one in parameter space, it would be 1/4, for example. And if you put C equals to 1/4 in this case, you will get exactly 3/4. That's what I want to say. And this is basically
These positions depends on the order of the basis function.
depends on the order of basis functions. What do you mean by order? The polynomial order?
Yeah.
I don't have my file here, but I will show it to you on Friday. I will repeat this concept.
One thing, just to clarify the notation, can we go to the page, like the last one?
Yes.
I mean, just because maybe I'm like confused.
Sorry for my bad.
No, sorry. No, the previous one. Is it, can you go down? Is it nonlinear dependency of x big or x small? It's x big small. No. So the last sentence. This results from the nonlinear dependency of x on c. I'm a bit confused there, and also like in the equation below and stuff. I'm just wondering like to have like the correct.
No, this is correct. I mean, this is, I mean the nonlinear dependency of physical space and parameter space, because x it refers the x coordinate, c refer to c coordinate. It's really
And also in the last equation, it's correct.
this one. Let me replace it to make it more precise. So this is supposed to be. Now you get it. So you should get it, right? This one. X, big X,
Of c.
of C. Yes.
Okay.
Okay. Yeah.
Thank you.
Thank you.
See you.